Welcome to the Wyoming Department of Environmental Quality, Land Quality Division's Blaster Continuing Education Training. Today is June 30th, 2020. My name is Keith Giel. I am the Public Information Officer for DEQ and today's moderator. Also with me today is Rio Barney, our Land Quality Division Blasting Program Manager. Before we begin, I want to remind all attendees that their microphone is automatically on mute. After each presentation has concluded, we will take questions and comments. To participate, you will need to raise your hand by clicking on the hand icon located on the GoToWebinar menu options. That should be on the right side of your screen. You can also type in your question in the question section of the menu. So without further delay, Rio, are you ready?
Good morning. Yeah, like he said, my name is Rio Barney. I am the Wyoming Blasting Program Manager for Wyoming DEQ. Welcome to today's session of the Wyoming Blaster Continuing Education Hours webinar. This is the second installment of these webinars. Just as a quick reminder, registering for the online webinar just gives access to the live class. To receive continuing education hours, the affidavit of attendance must be filled out, signed, and returned to me after the conclusion of the webinar. Preference is by email if you can. If you're having some issues with email, you can also send it to my address here in Sheridan, Wyoming. Here's the affidavit of attendance. Please fill this out in its entirety. More than one blaster can utilize this form at one time. Expectation for these is that you attend the entire session. If an emergency or something comes up, you're not able to attend, please just simply note that and the reason why you're not able to attend the entire session. And also note if you require a certification of completion sent back to you. This is not required for Wyoming blasters, as this will be on file with me here. Here's an example of the certificate of completion, name, and then the recorded date, what date it was recorded on, and date that the class was completed. So that one, I was there live, so I put June 23rd on that one. And then the number of blaster continuing education hours that were assigned for that. This is a new one from after last week's webinar. I do get a report on analytics for the webinar. With that, I get the time logged into the webinar, a number of login attempts. So I can, if you are truly having computer issues and computers crashing, we can actually see that. It comes out on the report. And then also, it also gives each participant an interest rating. So this rates how engaged participants are in the webinar. My intention here is just verify that you were in fact logged on to it, but also kind of maintain some credibility for the webinars. If one of your state agencies is questioning using the online webinar format, please just give them my contact information, and I can walk them through how I verify that you actually participated. All right, here's we had a session last week, June 23rd, for 4 hours. That session is available. It was recorded and available online. And then today's session, and that one will also be available in the recorded format as well. Then an announcement here. We did schedule the third installment of this for October 6th. That's in between elk hunting seasons for me, at least. So that's why it's October 6th. So a total of 12 total hours for these webinars. I go through today's schedule. We'll start off with Brad Brown from Dyno Nobel. He'll be doing bulk loading safety. And then we'll have Tony Truchon from Nelson Brothers Mining do explosive properties. And then the next several sections will be presented by Ron Eastman from NAX. That'll be geology and rock mechanics, detonation, shock physics, and rock breakage. And then the last session from Ron will be the sensitization and stemming. And then we will end with Mike Mann from Ohio DNR with the effects of microphone deployment methods on air blast measurements. And it'll be 4 hours for today's session. Also a reminder, this is for Wyoming blasters. Due to the COVID-19 pandemic, we issued a grace period for certifications renewals that started March 13th and plan on ending that October 31st of this year. And just also a quick reminder, we did have a blasting webpage that was launched last week. That is the address on the screen. You can also just search Wyoming DEQ blasting to find that page. And a big one there, if you'd like to get signed up for training notifications, you can go to that webpage and sign up through the webpage. I got a new form here. I went over this last week, but going forward, when you renew, you have to pick between a surface coal or surface non-coal blasting endorsement. Class schedule, got a class scheduled. This is a full Wyoming Blaster certification class, July 14th through the 16th in Gillette, Wyoming, and then again in Rock Springs later in the summer. There's my contact information. Please give me a call or shoot me an email if you have any questions. Thank you, Keith.
Thank you, Rio. Next up is Brad Brown. Brad Brown is with Dyna Nobel, and he will be doing a bulk loading safety.
And switching over, title slide, and it says I'm unmuted. Can anybody not see stuff? Can anybody hear me?
We can see and hear you, Brad.
Beauty, thanks. One comment before I get going. I don't know what you've got lined up, Keith or Rio, but I posted the link to last week's webinar up on the Northern Plains chapter SEE webpage, and we'll probably do the same with this one so that people can get access to it. I would expect it'll probably be up on that Wyoming DEQ page too as well, because that's news to me. Okay, bulk loading safety. I wanted to take a quick look at, obviously a safety topic is always good to start with, but look at bulk loading. Something I just added in there this morning because I woke up in the middle of the night thinking about it, and it applies across a lot of the states, every state. The safety of the loading crew, the personnel in the area, and the neighbors should be the first consideration. I know everybody's got them in mind, but you got to make sure that that's what's foremost in your mind as you head for a pattern. Best way to do this is to have a blasting plan and then to communicate it to everybody involved. And those are important words because it's often a legal requirement. Just talking before the seminar, Rio says, yeah, it's in there in the Wyoming requirements. You have to go out of the blasting section back over to chapter 2 when you typically get into the permit application aspects. But just about everybody listening should have a requirement there for a blasting plan. I pulled these particular words from our open pit blasting manual. Little history to get going, not to shun or push off on the package side of things. A lot of the business in the U.S. has moved from package to bulk. The little red sliver there is what's left of the package market right now, and that includes a lot of products out there. Package, we obviously talk about accessories like boosters and things like that, but stick powders of all sorts, shapes, varieties, and to an extent, some packaged blasting agents like the very bottom left, that bag of presumably Anvil that's sitting there. But the move in the industry has been away from packaged simply because of the cost and the manpower required to deploy it and going to bulk. You've seen bulk bins and things out there, and there's a variety of equipment here. Not all of the pictures I have are Dyna Nobel stuff. I've got a few really good shots of some other folks' equipment in here. So take what you can from it, look at different configurations, but more importantly, the way they're using it. The push with bulk is to get away from the backbreaking labor and to get more and more automated processes, more and more very controlled products in bulk form into the hole. So, for example, here we're seeing emulsions being pumped in the top, and in the bottom right, a blend in this particular case. Some of the numbers from the USGS yearbook, it's been stalled out at about 98% bulk AM based. There's still about 2% high explosive and permissibles in use. And for this year, this reporting year, 2017, just shy of 49 million detonators. The big push, at that time, we were about 58% of the explosives totaled going into coal mining. After that, you see the breakdown for construction, quarry, non-metal, and so forth. In terms of volume used, the reason I'm pleased to see Rio doing this is Wyoming, if it was a country of its own, is leading the pack with the volume in explosives. So better training for the people that use the most, hard to argue with it. Other thing in thinking about package versus bulk, are there different product hazards? Yes, but the keys are the commonalities here. All explosives are meant to explode, and a lot of people use the acronym FISH, friction, impact, shock, and heat. More Australians than North Americans, I find. But in any case, those are the hazards that you're looking to get past and avoid in any products here. But everything we've got is subject to those kinds of things. External forces like lightning and fire. We've had a couple of fires in the area recently. We had one near our lab facility over in Lehi, Utah, just last week, and there's a pretty good one down between two of the big mines here in the basin, just grass fires, but it makes you think about what you've got, and for example, making sure that you've got all the weeds and everything cleared away from the magazines or the storage areas. Safety data sheets have a lot of information on the composition, fire, reactivity. The whole point of this is to look and say, hey, what are the hazards for the specific product you're using? Anybody that's out there should know this. This is what MSHA, for example, would be quizzing you on. Now the thing is to move on to bulk and look at some of the specific things there. So, bulk products delivered, trucks on the bench, things coming in, different ways of delivering them to the hole. Different products there, from dry ANFO off a truck to an augurable blend where you've got a mix of ANFO and some kind, presumably emulsion blend, so you could use a water gel type product with it. Pumpable blends, higher on the emulsion content so that you can pump it in a hose using a water ring for lubrication, and all the way up to straight emulsions, which can be pump loaded into holes. But the idea is that you've got mechanical means to put product into the hole, and you can dial in what you need for the application. Probably one of the most important things, and this is a busy slide, but I like the way they pulled out a bunch of stuff here, the walk-around inspection. You've got a different kind of equipment, different situation, and after you finish your tailgate meeting or whatever else you've got going on, or presumably before you drive to the pattern for the tailgate meeting, you've got a lot of things to check on a bulk truck, but it's no different than anything else you do. You've got to look at your equipment, you've got to assess the situation, and you've got to have that log. I know years ago, Bobby had to get in some guys' faces because they were going to do their inspection report at noon. Well, that's not a way to do it with the inspectors running around. You need to have it done early and know what the situation is before you get a long way down the road. This thing's very busy, and I take it down and say, hey, what works for me? I walk up to a pattern, and clearly I'm not driving the truck. But as I walk up, I kind of look and I go, hey, what's important on that equipment as I walk towards it? Is it clean? That's a big giveaway, for example, for the MSHA folks. Do the lights work? Do you have the flashing lights and flagging and those kinds of things, as well as headlights on it? Do you have side lights where guys are working if they're early or late in the shift, especially in the winter? Going with the clean part, the leaks side of it. Do you have stuff visibly dripping? Do you have accumulations and that sort of jazz? And frankly, can the radio work? Does the guy know that you're coming into the pattern? Then you get into things up close to the truck. Do you have an inspection log if you're chasing after that? Does it have, these days, fire suppression of some sort out there? Do they have adequate fire extinguishers that are tagged, in date, that sort of thing? and most importantly, probably an operator, and not just a guy in the seat, but a trained operator, somebody who knows what's going on out there, who understands the truck inside and out, all the controls, all the sensitive points, all the metering points or safety devices that are in there and so forth. You've got to have them understanding all of that stuff. Here we are, different view, another truck, but in the upper left. So they understand the control panels and the mechanisms for dialing in what product you want, how you want it delivered, how much is delivered, and to record what you've got. Because in Wyoming, we require a hole-by-hole load for our blast report. But a trained operator is a key to it. Some of the people hazards I think of fairly quickly out there, because I spend a lot of time around the truck, but not operating it, and generally talking with guys, watching how things are going, trying to put other things down the hole, that sort of jazz. Getting hit by that boom is one of the first things that I see out there, and watching out for it. A truck moving with a boom out there has a chance to hit people, or more seriously, sweep people over cuttings piles or bumps or whatever's out there, or for that matter, push them out towards the edge or over the high wall. It's not common, but that boom is out there, and it's an obstacle that can come at you in a hurry. The other part, for the pumping side, the hose reel can also hit people, because you've got some hydraulics things pushing out there, swinging, moving, and so on, and you've got a hose that's there swinging and can get hung up or tight in the hole or tight as it's reeling in, plus you've got some rotating parts. So those are the obvious things that I see when you get up close to the thing. The hydraulic controls, yeah, there have been a few minor incidents with guys where you get pinholes in the hoses, and you get jets of hydraulic fluid coming out and knocking the glasses off them or catching them in the back of the hat or something like that. But this can happen on dewatering units and a lot of other equipment. But the idea is you watch out for the different things that might exist on the bulk loading equipment out there. I see this picture as staged. Guys standing there looking serious in a way, but they're on the opposite side of the emergency stop, and I don't know what the mess behind them is, but I don't see what purpose they're serving out there. So I watch out for where people are relative to the booms as trucks are maneuvering and as things are operating. On the hardware side, just about every truck out there, doesn't matter who's made it, whether it's Tread or TradeStar or whoever else is out there, they're worried about pumping products through the thing. And what some of the sensors go towards dry pumping, trying to measure when there's nothing in the pump itself, and you spin and spin and spin and build up heat. Deadheading, where you've got the pump running, but nothing is happening. The product, there's a blockage or something keeping from product moving, and you build up heat in there with product in the pump itself, creating a problem. Heat buildup in general, there are systems that have heat sensors around the trucks. An alternative to some of these things is a flow meter that will actually check and monitor flow and can tell you more about these things. But in any case, you've got some collection of sensors on most bulk equipment these days that'll protect the equipment and protect the operator and the people around it. Some of the transport equipment issues, obviously, would be around the augers and hoses, covers and guards. And the things there are very simple. You don't open covers when things are energized. You don't put your hands or anything else in when something's energized and moving, and so forth. And that goes back to just a trained operator, some basic safety things. There's obviously maintenance that goes on with the augers and the mixers out there. I don't like the picture because it's got a guy between the auger boom and the truck, but there's got to be a reason for him being in there doing it, whether it's just that flat spot for the density cup, the density check. Whatever it is, though, I kind of look at a confined space there, a tight space for a guy to be working in. On the equipment side, maintaining things and keeping the bearings and the flights and everything working properly is part of the job, and it may take some attention out on the bench, or it may say shut down this unit and go get another one and bring it in. Calibration. You're expecting the truck to do a lot of the work for you here by putting the right components together and getting the right product down the hole for you. It's there to ensure the intended product is delivered, and it involves calibrating a bulk truck, involves tuning various parts for delivery so that it goes as planned. but the operator has to understand and has to be aware of and reacting to things like wear, weather, product source, time, and so on, that may say, hey, I got to tweak this, I got to double check what I've got. One of the big ones I think we talked about in the previous session on some of the products, and Tony can talk about it in properties, is product source. If you've got breakdown of prill because of the seasons or because it's been handled a lot of time, the density of that prill that you're blending with may change. And you may see the need to adjust based on what you pulled out of a bin and put in there. That's all I'll say on that one. A lot of the electronics these days make the calibration very simple. Some of the newer, smarter trucks can look at the products and check things for you and work on that calibration side of it. They can get a predetermined sample and they can record it for you as well. Some of the systems and the logging systems require an operator or blaster to take a density and record it. That's not unusual, but it is possible to have that density recorded at a given hole or points along the shot there. The system can also automatically tune some of the parts to adjust for what may be going through there. The density checks help ensure the delivery system does deliver what it needs, what you're asking for, and it can also alert you to a problem out there. Again, depends on how smart the system is, how it's been built. But these things can be pretty good at giving you a consistent product. A couple of words on driving on mines and patterns, because I've got a whole bunch of things here on this. Probably number one in there, and comes from a previous life, communicating with mine traffic. As the blasting engineer down at the site here in the basin, the call was always up from the production folks that such and such a truck did not call in and tell them they're entering the work area. Well, I've got both ways there, because I'll tell you what, they get tired of you calling every time in and out of there, and you are part of the workforce in that area. But communicating with the mine traffic has to be a frontline spot there, a premier spot for the operators. Got to let them know you're coming, let them know what's going on, particularly if you got a whole herd of people coming in, or like all good blast patterns, if you're going to attract a herd of people to come in and stand around and do the Hummer routine. Roads, ramps, berms, I've got some things on that, but the simple parts are conditions change, and there's not many blasters around here that have not had the experience of being on a slippery ramp, whether it's wet or icy, or face going down a ramp a little too fast for whatever reason and see a high wall coming up real close to them. But those sorts of things. The other part is berms and the protection that's there. We've had a number of presentations, for example, from MSHA and others, talking about necessary berm heights, and for that matter, berms and blocked entrances to blast patterns. That's got to be in your mind as you approach a pattern out there. Some words on trucks and drills, some initial driving over products out there and working under high walls. The whole smash really comes down to part of your take 5. You've got to decide that you've got to head out to a pattern. You should be assessing the road conditions, assessing the situation as you approach it, and you've already made some adjustments to it. You may have to do it again and say, hey, how's this ramp look? Is this going to be okay to go down? But communication, I find, is a big part of it, and doing the take 5 to protect everybody there, including yourself and the equipment, is what's needed. Heading to the pattern. This is way back. This is road conditions. This is an icy road over in Georgia, and they've separated the bulk tank from the bulk truck, which is not a good situation, and the towers and everybody else are trying to pull things around and get it back into shape. Assessing the road conditions is what I focus on here. You wouldn't expect ice in Georgia, but there it is. And out on our mine sites, we can see everything. We can see all 4 seasons in a single day. Getting to the pattern. I love this shot just to tell you that it's not going to be your normal day getting out there onto the bench. You've got to assess it, make some good judgments on what's worth trying to do, how you need to make adjustments in your workflow, how many people you're going to send, whatever it is that this says to you, but you got to be careful getting out there. This is an old shot from, I'll call it Brand X, and I blocked out the logos on it. Quarrying situation in the east as it came through our safety system long ago. And the ramp was dug out Monday morning. They'd just been in the area on Friday, and Monday morning, whoop, no more ramp. So they put themselves in an awful situation, not knowing roads, road conditions, changes in the mine, that sort of stuff. One of the mines I visit has a weekly road map available. It comes out every Thursday with the most current photo, and it's got some changes on it, and I like to get one of those as frequently as possible so that I can see what's changed when I'm headed out. Different situation I was in. I actually had the thrill of having a consultant visiting while he was in the area, and I took him out to where they were loading it one afternoon. Muddy little spot. They had a ramp into the blast area, but it deteriorated. Soft material was pushed across a big ditch, and as the trucks and everything ran across it, they just smushed it down. And it got to a point where they had to have a dozer pull the bulk truck out of what was going to be an awful situation and then rebuild an access to it. Never be afraid as an operator to get a proper access, whether it's a ramp adjusted because it's too steep, and some of them are too steep, or just getting it watered or scraped up a little bit with a blade. But protect yourself. You're getting onto a ramp, and you need to treat it like an interesting situation. Problems on the pattern, whether it's part of your tailgate meeting out there or somebody going out to inspect the work area as part of the MSHA side of things. You want to know what you've got, and preferably know it before you get there. If it's just water, if it's a lot of mud, if you need to skim stuff, if you need to change the situation to make it work for you out there, do it. This is going to be an ugly coal pattern to get at, but it's not the worst you've seen. You've probably seen lots of stuff out there that really doesn't help you out. This is going to be a problem because some of these holes will never get dewatered, so it's going to take some scraping, blading, ditching to get things to drain effectively. So it's going to have a big effect on your plans, and if you don't take care of it, it's going to really make a mess of performance. Congested patterns. You're out there, you're working, you've got a sweet deal going. It gets busy in a hurry. And this one, what do we have? 1, 2, 3 drills in the area there. Bulk truck, blaster's truck. There is a bobcat hiding out over there. Wouldn't surprise me that there's a dewatering truck somewhere, except the dust says it's fairly dry. But you've got a lot of things going on out there, and the idea is to protect yourself, protect the other people, and know where it's safe to maneuver, what you should be doing. You've already got some holes tied in there. You've got flagging that shows the advance of the initiation tie-in. You've got to understand what's going on out there. And as what I often call myself a visitor on these patterns, I'm there because the blasters allow me in. You've got to be talking with them, and you also have to be aware of the hazards. And at some point, you've got to say, hey, too many people, let's clear this place out. We're gonna start moving drills, or we're gonna take on something else. You got to protect yourself out there. Too much traffic on the pattern. I grabbed this old fatalogram. I saw the picture last week in one of the things. But this is just flat too many people out there. A surface driller was injured on a gold mine. He was struck by a pickup truck there when he was walking around. Things will happen like that. You get too much traffic and things going on. The analogy that I look to on the bulk side is you've got a bulk truck or multiple bulk trucks chasing around the drills, if you like, or working their way through a pattern. You've got dewatering trucks that may be moving through the area or moving in to pick up something that they didn't know was wet. You may have other equipment around there, maybe lining holes, or people out there with equipment trying to do things, but you got to keep control of all of that sort of stuff and keep the unnecessary stuff out of the way. The trucks versus drills deal. Saw this in several ways. I just picked a simple one here. Talking with a guy years ago at a drilling conference, he said, what's the slowest moving piece of equipment on the mine site? Typically the drills. What piece of equipment has been involved in more incidents on the mine site than anything else? The drills. They walk into things, they bump into stuff, they just go all over the place. This one was proximity of a drill, electric drill in this case, and a bulk truck. And it's all big iron on the drill. You're really not going to hurt the thing unless you really smash an electrical component or something like that that's going to drive it. Same kind of thing with a diesel run machine. They're pretty hard to bump and to do damage there. But catching the bulk truck itself and damaging the auger or the vertical sections, denting, or worse yet, puncturing a bin. Those kinds of things can get interesting out there in a hurry. Not a lot of damage on this, but the goal on the thing should have been to plan the work in the area, keep the trucks away, whether that's demarcation or whatever, but plan the moves, plan the access. With an electric, it's obvious you've got to stay well clear because they're cutting off your access to half of the area where the cable stretches out. Communicating with the driller. Let them know you're coming in, let them know you're making a pass somewhere, and for that matter, the driller telling you that he's going to pull out and head out of there. Demarcation, used data in the previous life to show where holes had been loaded, where things had been tied in, where the drills were going to work, where the bulk trucks were allowed to go, that kind of stuff. Spotters out there for both the bulk trucks or for the drillers when things get busy. Here's one next phase, driving over initiation products. And there was one of these in last week's deal. This is one from property I was associated with. Things getting in close there. And in this case, they had to make adjustments on the pattern. It got tighter, but for whatever reason, as equipment's moving around there, the bulk truck's maneuvering around on the pattern and runs over an MS surface delay connector. That is one of those double-ended initiation products, and it's got presumably some cord in there with it. You see the block over here on the right picture there, the blue block and stuff there and stuff covered up. For whatever reason, when you get in close, you've got to watch. This is where the spotters may come in. This is also where a procedure for driving over a loaded hole may come in. A lot of people would say, hey, you're supposed to have a written procedure. I'd like to say you have a written procedure and it's on board the bulk truck or the dewatering truck if they're going to go over a loaded hole. And that's coiling up the product, the initiation system if it's there, burying it in some stemming, putting something over the top of the hole, a board or whatever you have, or enough cuttings to protect it. You still have to dig it out later, but you've got to have something there to protect products on the bench. Another one from previous life, tough picture here, but dead center there. You see a sloughing area of a high wall, end wall on a coal, above a coal shot for, in this case. You've got a dewatering truck down there on a coal pattern, and it was just somebody spotting what's going on and doing the right things, saying, hey, this is not a good place, not good to be under this pattern. Call it, put up a berm, keep people away from it. Some of the mines have requirements that you stay away, rules, hard, fast rules that say you stay away from high walls and so forth by at least X feet. Credit on this photo to the Nelson Brothers guys. I love this. Instead of having the truck sideways and the cab operator not able to see what's going on, they've got him pointed out. Instead of having the blaster on the ground between the truck and the high wall, they've got him at the side, able to get away and able to view up the wall to see if there's something going on that needs his attention or needs him to start moving his feet real fast. Getting the alignment there, and this comes down to planning, but getting the alignment there so that you protect the people is not only something for the bulk truck drivers and the blasters, but it's also thinking about the drillers. Don't get caught with your cab between the mast and the rock, mast and the high wall, those sorts of things. Planning on it, communicating, making sure that it works and you protect people is part of the job here. Some of the bulk loading checks, and just a piece of art on the right there. I go all the way through and look at drill reports. You should have something from the drillers. I don't care if they're working overnight, if they're a step up or something's changed there. They should be able to tell you something about what they drilled. Did they drill through the rock? Did they hit soft zones, that sort of stuff, lose their air, that sort of jazz. Anything there. And as you approach the bench then, are there any new face sloughs? If you're going to put a lot of product in the hole, you want to know if the burden has been reduced overnight. You obviously have to be out there bobbing holes, working things there, looking for proper column rise, and worried about overloading. Bobby talked about that last week in doing his powder factor and borehole rise calculations. That's just a core part of the blaster's job, but more information helps out. So knowing something about water or any gaps in the material that's there, gaps in hard rock, that'll help you. And floating primers when you're running bulk is an obvious one. There's a whole treatise on that sort of stuff. The goal is whatever product you're using, get it seated properly, get it in good material, good explosive product, and check your initiation system as best you can, whatever it is, before you get to stemming the hole and moving away. Ron Eastman would say that bobbing holes is probably good exercise for fly fishermen there. He's got a nice loop forming there, but you got to be checking what's going on. You can't just let it run for X amount of time or hope that it's hitting it and just quit there. There's too many stories of guys out there with, I put 3,000 pounds in it and it's still not coming up. Well, now you got to get a sucker truck out or something to get product out of a hole or to alleviate a potentially dangerous situation. Pinking out the hole. Kick a little dirt over it and nobody's the wiser. I think we talked about this a little bit last week. Overloading a hole, you got to own up to it. You got to tell folks so that you can clear things out, or worse yet, get the product out of the hole. But you've got to be able to manage it and protect people. That goes right back to that very second slide there on the safety, the people on the bench, the people around the blast area, and the neighbors. It's not better blasting, it's sloppy work, and you just got to own up to it and save a bad situation from getting worse. Overloading, potential overloading, I should have said here. This is no shot in particular, but I grabbed it because it had some opportunities in here, and it'll cycle for me in a second. You got to wonder, is that a fresh slough on the face? Is it something that was missed in the original survey or something that needs to be looked at before you continue loading in there? Some people will say you don't want to load a face until the very tail end in case something sloughs off. The other things going on in there flow through from it. Did the driller give you some information on it? Were they a step-up driller, and did they lose air somewhere there? Did they have a problem with the thing somehow, some way? Enough of that one. Overloading, I looked at it another way here as well and said, hey, we talked about a bit about worn bits, and bits aren't all exactly the same. You take a look at hole sizes, and I drew these roughly to scale here in there and said, look, we're going to load all of these with a standard blend, 1.3 grams cc. If that bit is worn, the blue bit, it's worn down or lost a gauge tooth or something like that, started at 12 1/4, it could be down to 11 1/2 or less. At 11 1/2, you run your numbers for that bulk product in there, you're about 58.5 pounds a foot, or 12% below what you wanted in the hole. That's not going to help your blast move. You're short on energy, and you may end up pushing material up in the air instead of forward the way you want, or getting the brake to the floor, whatever it is. It's not going to help you. A new bit, going by the specs there, 12 1/4, should put you in around 66 pounds per foot, and you'd know it. And you'd be working on that basis. That's where your design is. That's what you expect. The red, the oversized hole, if the hole is wallowed out, the bit is wandering around in there, you've got bent steel, you've got something going on where you're taking out more material as you drill the hole or as you clean the hole. You could be up approaching 75 pounds a foot, or better than 12% increase on it. I did the numbers on it at a 13.5 inch because I've seen that with some borehole caliper readings. 13.5 inch for a good portion of the hole will put you at about a little over 80 pounds a foot, and better than 21% more material, more explosive product in the hole. Anybody's got a pattern that can take 20% extra loading in it is something that's going to be interesting to a lot of folks. You shouldn't have that kind of range in what you load. Fire safety on the bench, almost done here. The obvious things: no smoking. You got to store materials properly there, and you got to control access to the blast site. I talked earlier about berms and so on, but just keeping the folks back, keeping them clear. In terms of storage of smoking materials, some of the mines have had mailboxes and stuff on their signage outside the pattern for years. I see some mines have ammo boxes or little cubbies or something like that to put smoking materials in before people come in on the pattern. A lot of guys will carry their stuff in their lunchbox on the vehicle, but they will get out and they will walk to the berm, walk away from the pattern to go burn one. A lot more guys have quit smoking because of it. But whatever it is, you got to control the flammables and things on the bench. Suppression on bulk trucks has become a big topic. There have been a number of bulk truck fires recently. That's where I go to the clean sources of heat, the operator knowing what goes on, but mines are moving on and saying, hey, we want suppression systems on trucks, including contractor equipment. I've heard of this, some in the area, but all the way up to Nevada and some of the things in the east, the Midwest coal operators and so forth. Whatever it is, the MSHA folks will tell you that you've got to have training on these fire suppression systems. You got to maintain the things, and people, the blasters in general, have to have a good understanding what their response to fire suppression system alarms should be. You got to know how the thing works and what your action should be, and that's not something you can make up on the spot. You got to know it, train it, and have the guys plan for it. Lots of control systems there, lots more things to inspect. You do that walk around. You have tanks, you've got pressures, you've got cylinders and tagging and so forth, all hanging on those actuators, the controls, nozzles, hoses, you've got chemical tanks, everything needs to be in good shape through there. Some of the higher end systems go with heat tracer lines, so you don't just have an extinguisher system there, but you've got something to detect heat buildup in around there, and the maintenance tags. As soon as an inspector shows up, they're going to be looking at the maintenance tags, and they're grayed out the process monitoring, because some of the very advanced ones get real busy checking what's going on the equipment. I'll leave that to the smart trucks there. The big thing is for operators and others around there to understand what should be on the truck, what looks right, what looks wrong, and have the people protected. Some of the operators' goals out here: prevent a bad situation. They got to know what the information sources are. If there's lights on, alarms going off, they got to know what that means and what's going on. Most importantly, they need to know what to do when there is a vehicle fire. Hit that e-stop and get out of the vehicle is generally the rule there, but sometimes you get one out of two. Whatever it is, you should know what you should be doing. You should protect yourself. Don't start trying to drive off the pattern unless that's your procedure, for example. But deal with the thing as fast as you can and protect folks there. If somebody's calling a mayday, the blaster in charge and those kind of folks should be looking at a bulk truck and saying, okay, that's not a place we're going to sit. We're going to get away from there. What is around the truck? Are there boosters in a box hanging on the boom? What's going on around that truck? That's part of the guidance for responders. You want to be able to tell people what to expect as you clear out the area. In a conversation with some folks a while back there, we said, look, the blasters know an awful lot about what's going on, and they do a really good job. They should be prepared close to the blast site to tell any first responders what they've got, what to be aware of, what the situation might be. It's just a tire fire, but we can't control it. So whatever it is, they've got to give some guidance to the first responders. But I've also said the further they get from the pattern, the less in control of it they are, and the more the first responders have to take over the thing. And in another talk, we said, hey, the first responders need to recognize they don't run in to fight explosive fires. So good understanding of what's going on. That's part of what happens with some of the bulk equipment. A couple of references and things here. Last slide. The IME, Institute of Makers of Explosives. It's an industry organization, so it's groupthink, putting together a lot of good documentation. These SLPs that they have a lot of good stuff. I just grabbed 4 of them here. SLP 4, warnings and instructions, that's pretty generic. 17 goes into the safety side, particularly of bulk use, because it's a big and bigger part of the industry. 27, the security of, in particular, bulk. And 28, very much focused on accountability and security for bulk operations. They do cover packaged, but 98% of the market's gone to bulk, so these are very good resources to at least understand so that you can operate a safe blasting operation. The always and nevers, we've talked about those things, and obviously the federal, state, provincial, and other local regs will come in. That's what I had here. I see one question there. Just to ask if you guys have any questions. How many drillers have run over their own pickups? Rio's asking. He's asking for a friend, I'm sure.
Usually
That's what I've got.
Usually don't get too many takers on that one.
Questions? Comments? issues there?
Hey, Brad, I don't know if you can hear me, but I just wanted to comment on that one slide with Nelson Brothers where we were doing everything right. Another thing we've implemented is especially on bad days with freeze and thaw and all that stuff, we've actually put spotters out there with air horns. As soon as that air horn goes, if the spotter sees movement, you drop and run, and that saved our butts multiple times. And then also on the slide that you showed with the face blowing out, as it looped around, you could tell obviously where that sloughed. And you know, that's a huge thing there. I've actually seen where the pattern's been designed. They haven't drilled on it that day, but when they go out to drill that face row, there's been enough sloughing. They actually, on a 30-degree angle, have drilled through, and you can actually see daylight. So that's a big one too, but a really good presentation.
Thanks, Tony. Good comment, and I really did like that picture of the guys there. I know about the guys with the air horns and the spotters. That's an excellent way to do it. You've got to look at the wall, you've got to assess the workplace, but now you're putting equipment in underneath. It's probably not much different than tying in with cord and things under the high wall. To be the last place you want to go, it'd be the place you want to get people away from as quick as possible, but you got to protect those folks. On the blowout stuff, I like that one because it opened up a bunch of questions. Could there be something in the drilling if they overloaded? That was one discussion that I've had in several places. The sloughing, we used to see that in some crummy ground down south here years ago. And the guys would go in and say, hey, we're going to go load that face row today. I need a scan and I need to see sections cut through every hole. And I'd have those delivered to the blasters so they could look at it and they could say, yeah, I can't load the full hole, but I can load this much. I can load here, stem through this, and reprime and load some more. Or it's just all too tight and I've already got it loaded. I got to change the timing, those kinds of things, to let the side holes go out and then fire the one with reduced burden. Whatever it is, you have to have a plan for it. Bulk loading is not dangerous. It's not a bad situation, but it just gives you different things that you've got to account for. And you've got to be prepared to do the work to get the right energy against the mass applied in the right time frame. So thanks for the comment, though.
Brad, this is Keith. It doesn't look like we have any questions or anyone has raised their hands. If they'd like to ask a question, they can do that through the system or raise their hand and we can call on you.
Good deal. I'm done, and I think you have a break planned.
Yes, we do. Thank you, everybody. We'll go ahead and let's take about an 8-minute break. Let's get back at it about 11 minutes past the hour. Thank you.
Okay, let's go ahead and get restarted here. Next up is Tony Truchon. He is from Nelson Brothers Mining Services, and he's going to do a presentation on explosive properties.
All right, thanks, Keith. And before I get going, I'd like to thank both Keith and Rio for this opportunity. We did it last week. It was a great success doing it this week. As a company, we like to get like 4 hours in the spring and 4 hours in the fall to our employees, our blasters. And that coupled with our local chapter, ISE, which is called Best and West out here, that brings South Dakota and Wyoming together to, get the hours for recertification. Well, with everything going on and COVID-19, it's very difficult to do. And our company policy won't really allow us for group gatherings, and we have to wear masks. So this is a great opportunity for us to continue our education. I see we have some people from this week that weren't here last week. My name's Tony Truchon. I'm with Nelson Brothers. I've been in the mining industry since for 20 years, and I've been with Nelson Brothers since 2008. I'm a tech rep and get the opportunity to share explosive properties with you, so I look forward to it. So let's start. Definition of an explosion. This comes straight from Wikipedia. An explosion is a rapid increase in volume and release of energy in an extreme manner, usually with the generation of high temperatures and the release of gases. Supersonic explosions created by high explosives are known as detonations and travel via supersonic shock waves. Subsonic explosions are created by low explosives and through a slower burning process known as deflagration. So through my training, another way to define an explosion is just chemical reaction involving an extremely rapid expansion of gases, usually associated with heat, the liberation of heat. But having said that, what we do, we deal with high explosives, so we won't really deal much with deflagration. An explosive is a combination of various substances and mixtures that produce a rapid exothermic reaction when initiated. Exothermic just basically is release of heat. So we'll get into explosive classifications. Now, the most common oxidizer that we have out there, and Brad's kind of jumped on this, was ammonium nitrate, or AN. That's what you'll see most there. It is manufactured. It's just basically in the solid form. It just comes as a prill. They use it in agriculture as fertilizer, although it's produced different in the industry, mining industry. The prill that you'll see is more porous to accept diesel fuel or whatever fuel that you choose to fuel and make it a blasting agent. And usually your ag grade will have some type of coating on it that allows for more of a time released out in the field. And once you put fuel oil, like I said, then you start getting into a blasting agent. So ammonium nitrate mixed with fuel is AMFO. It cannot be detonated with number 8 blasting cap, but when you're looking also at a blasting agent, your oxidizer can also be ammonium nitrate solution, and that with a emulsifier and the fuel, mineral oil, whatever, you can create an emulsion at that point. And if that's not sensitized, then that too is considered an oxidizer. But as soon as you start sensitizing it, adding gas or bubbles or whatever, then you're now a blasting agent. Then your high-end explosives are detonators, boosters, surface delays, things like that. And what do explosion, what does it require? It's much like the fire triangle. You need and if I go back here, you need your oxidizer, ammonium nitrate in this case. You need your fuel. If you're just doing straight AMFO, usually it's diesel fuel, but you can also use used oil. And your ignition source, which is your detonator and your booster. Around here, the explosives and oxidizers, and I think throughout the mining industry, because Brad's already kind of talked about the bulk versus package, and it's primarily all bulk. You have the AMFO, which is your AN and diesel fuel or used oil, and then you also have your emulsion, which is an AN solution, and oil, of course. With that, they don't mix, so you need an emulsifier to combine them, much like the process they like mayonnaise. You need to have something that makes those two meet or mix. The intimacy between fuel and oxidizer influences the explosive efficiency. So just sticking with AMFO, Brad alluded to this a little bit, but we're just going to use 94% of your prill, 6% of your oil. That's kind of right in the range. But like Brad alluded to earlier, if you have a prill that's been transported and pumped and went through several temperature cycles, things like that, it's going to start crushing that prill. And at that point in time, you're going to have more surface area. So you're going to have to increase your fuel oil, to get to that optimum, which I'll go over a little bit later, but you're kind of getting to that oxygen balance. So I'll go over that a little bit more in later slides, but your prill is a big influence on how much diesel fuel that you need, and you need to monitor that. And if you're getting prill from different sources, just make sure you know what you're getting and how to fuel it. We went through detonation versus deflagration, but I'll go over it again. Deflagration is an explosive reaction that moves through the explosive material at a velocity less than the speed of sound, and then detonation is the explosion consisting of an exothermic release of heat reaction, which is always associated with a shock wave greater than the speed of sound. So when you're looking at detonation, you'll have that shock wave that goes through, and it's going greater than the speed of sound. I'll get into that a little bit more here. But the characteristics of explosives that we deal with, you're going to have detonation pressures at anywhere from like 150,000 up to 4 million PSI, temperatures from 3,000 to 7,000 Fahrenheit, and your VODs or your detonation velocities, you're going to go from 8,000 up to 26,000. We go over that a lot. VODs are a very important thing to judge how you're doing out in the field. So, and when you start looking at like your 4 million PSI, that seems extremely high, but that's more like in your CAS booster, things like that. So we'll go over all that. Important characteristics of detonation. So you have that fast release of energy, and it generates that shock wave. And then right behind that comes a large gas pressure. So basically with that shock wave, you're fracturing your rock, putting little fractures in it, and that gas comes in and fills those cracks, and that's where you get your fragmentation. And the explosive properties that we'll be looking at today, we won't go over everything on this list, but here's a list of things. And like for number one, we probably won't go over temperatures, but temperatures are more related to your bulk products that are more liquid. So the lower the temperature of like your emulsions and things like that, the less sensitive it's going to be, and it's going to take more energy to get up to that state where you can get that explosive reaction. Temperatures really don't affect your solid, like your CAS boosters or your prill, things like that. The more of your solid, it's more liquid based. Shelf life is another one we probably won't hit on, but that's just, you talk to your manufacturer. There's a shelf life to explosive. Make sure that you understand that, and basically that's the maximum time you can have it before it starts losing its effectiveness. That you talk to your manufacturer, and when you're doing going through like your magazines, stocking it, make sure you use the oldest stuff first. Like I said, velocity detonation is a huge thing that we do a lot of testing in the field to make sure that we're getting good results. VOD is an important indication of efficiency, and it's the rate at which detonation travels through an explosive column. So it's basically time over the explosive column. And here's an example. This is an emulsion that we did. It's a pretty solid trace right there. There's not anything that really disrupted it. If there was, let's say, as you loaded this column in that 30 feet, you happen to kick in some stemming or something like that, you would see that. And you can see we got to a steady state pretty quick. So kind of showing us we're using the right primer or booster, and it's a pretty solid VOD. So we do these, and all manufacturers do, just to make sure that the bulk product we're putting in there is performing the way and as efficiently as it can. Factors affecting detonation velocity, we'll go over. We already kind of did the oxidizer fuel interface. Confinement, that's one where it'll affect VOD. If you're confined, like your confinement's not that great, your VOD is going to go down. If you have more of a strong, like a rock borehole, things like that, your VODs will go up. We went over temperature already. Product density is huge. And one thing to know on product density, and I'll go over and over it, as your product density goes up, so will your VOD to a point, and I'll go over that as well. And then the diameter of your hole and oxygen balance. So here, starting with velocity of detonation in that borehole, I'm just going to use AMFO at a steady state here. And on this, I don't know if anyone uses a 2-inch hole. You're getting pretty close to critical diameter, which we'll also go over. I don't know, I've never shot anything that small in diameter, but it's here just to show you how your size of borehole will increase your velocity, or your feet per second velocity of detonation. So at 2 inches, you're at 10,000. Once you get up to 12 and over, you're getting up to 15,000. So just a good illustration of how your hole diameter will affect your VOD. All right, we'll jump into density here, and that's just weight, mass per unit volume. And that's always expressed in grams per cubic centimeter. And the one big one that you need to know is water. That's we deal with water on almost everywhere. So that's 1.0. Of course, it could be higher than that if you have a lot of sediment and stuff like that, but water in its pure form is 1.0 grams per cubic centimeter. So when you go down, you look at AMFO, I just put a range there. First thing you see is, hey, wait a minute, that's lighter. Basically, AMFO is not going to sink through water. And so then you start looking at different ways. If you have a huge water issue, obviously you need to take into account for that, whether you can efficiently de-water. You might have to change your product there, but the emulsions, typically depending on how you sensitize it, things like that, you can get easily above that 1.0. And then to get the both the AMFO and some water resistancy, we go into blends, and blends can be, I've seen them as small as 10% up to 50%. You can even go more than that, but that around 50%, 45, 50% is where you're pretty sure you have a water resistant product, and your densities will allow it to penetrate water, get to the bottom of the borehole. I already said it. Density rises, so does your velocity of detonation to a point. At that point, basically, it's called dead press. You can get dead press in a couple of different ways. Dead press, if you're loading into a real deep hole, the pressures as you go down increase. Also, the stress wave from a previous or a borehole adjacent can also affect that, take that, desensitize the product, basically knocking those hot spots or voids that's below that out of the product, not allowing it to detonate, but probably getting to more deflagration. Hot spots, that's another good one. Those are the voids that we were talking about. So like in the prill creates its own, you already have, your voids created in prill. You add 6% diesel fuel to that, and you got something else shoot with a booster. Like I said, in your emulsion matrix, you'll need to add something. You'll need some people gas, some people add micro balloons. There's other things out there that can create those voids, but we'll go off. Energy partitioning is another big thing, and that's shock energy or the brisance versus your heave energy gases. Emulsions tend to have more shock energy, whereas your ANFO has more of that heave energy gases. And when you combine the two, it does create a nice balance between the two. That heave energy is really nice around here for casting. And the shock energy, we use, I see straight emulsion used, like in harder materials, rocks, things like that. But basically, that's your energy partitioning. Detonation pressure is down below here is your highest measured or calculated pressure. So a function of density and velocity of detonation is basically your density times your VOD squared. And here's some detonation pressures that you might see out there. I kind of went over that. Like I told you, cast boosters are going to get you more into that 4 million PSI. Well, if you take 240 kilobars, take that to bars, so take that times 1,000, and I think the equation to get that to PSI is like somewhere around 14.5. I should have looked that up, but that should get you up above 3 million, almost to 4 million. So that's where you get those higher end PSIs. But you can see your emulsion and your ANFO, what type of detonation pressures those would create. Your borehole pressure is 30 to 70% of your detonation pressure. Now this is from a training that I had previous. If you go through ISEE, it's going to be like 45 to 50% so of your detonation pressure. So that number might vary, but let you know that, hey, borehole pressure is going to be significantly lower than your detonation pressure. Sensitivity, I won't get into this big, but it's your ease of initiation and ability to propagate, and gap sensitivity is a test that they do out there. Basically, with density and sensitivity, as your density decreases, you become more sensitive. So like I said before, as your density increases to a point, your VOD will go up, but your sensitivity will increase as your density decreases. We'll get into critical diameter versus, and I put optimum diameter in there. It's not something that we really look at a bunch out here, but the critical diameter that's minimum diameter to sustain propagation. So you can get to a point where you're not going to be able to have that detonation and carry that detonation front all the way up through if you get way too narrow, or your diameter becomes way too small. Optimum diameter, I guess it's out there where the explosive output properties are maximized, and I don't want people to go out there thinking, okay, there's an optimum diameter, we need to design around that. That's just something I put in there because it was out there, but it's something, critical diameter is more important. All right, so we're getting into energy, and that's a measure of the potential for the explosive to do its work. Now, energy is hard to calculate, but there are detonation codes out there, the IDEX and the CPEX. The IDEX is, and I'm not super familiar with all this, but it assumes ideal reaction, so everything's perfect. And you'll find that information, that's the information you use for your data sheets that are out there. Also, I have never got to do this, but I've seen it where you measure basically your energy release, and those are in those pond tests. I know most there's places where you can go do that, and basically you detonate underwater. You have instrumentation set up to do measurements, plus you have bubble tests. See how much for your gas. See the bubbles come up after the explosion. And then when you're doing the energy expressions, there's two different ways we do this. There's weight, which is in grams, and then volume in cubic centimeters. And I'll go over this real quick. So your absolute weight strength, the absolute amount of energy available in each gram of explosives. So ANFO, weight pound per pound or gram per gram, ANFO is very, very strong. But it's also light. So if you're trying to fill, 5 foot of borehole, let's say, and you're looking at, we'll just go with the 0.82 density versus then you get into your volume. And that same 5 foot, you're going to put emulsion in there, let's say at a 1.2, 1.25, you're going to get a lot more pounds in that 5 foot than you will with ANFO. So there's a good, that's why there's the separation between bulk strength and weight strength. So relative weight strength. Now, what we're doing is we're the same thing, but now we're comparing it to something, and we compare it to the standard ANFO, which the relative weight strength on ANFO is 100. So we're comparing everything to ANFO on that, and then you get your relative bulk strength. Now there's the calculation here to come up with your relative bulk strength, and it's your relative weight strength time your density density divided by the ANFO density, and I just put a range of ANFO density below there. You'll want to check and see what your ANFO density is, because once again, with different prills coming in, and it'll vary. More fines means your density is going to go up. They actually even used to make heavy ANFO and package it to sink water. I mean, they'd basically grind the prill and try to get that above the 1.0, package it and throw it down there. I've never been around it, but I know it existed at one time. So just to go through that calculation real quick, this is just a fictional product. It's nothing that Nelson Brothers sells or anyone else I know of. I just threw some numbers out there, but your relative bulk strength would be, let's say the absolute weight strength was 95. The density of the product that you're looking at is 1.25, and the density, the ANFO that you want to compare it to is a 0.84. So you go through that calculation, you come up with 141, or it's 41% more strength than ANFO. So that's a pretty simple calculation. The next thing we're going to go over is water resistance. That's a huge one. Like I said, ANFO's lighter than water, but the other thing with ANFO is it deteriorates in minutes or seconds with water. And I wanted to bring in a video, but it's just way too long, that we did at Nelson Brothers. But basically, we had same size cylinders, clear cylinders. We loaded one with ANFO, one with a 30-70 blend. And when I say 30-70, I always use the emulsion percent first. So it's 30% emulsion, 70% ANFO. And then we did a 50-50. And we introduced water, and the ANFO broke down just immediately. Then you started over time, you could start seeing the 30-70 going away, and then the 50-50, well, we could have went on for days and weeks. It was holding true, because like I said, at the time you get up to around 45-50% in most cases, you have what you call water resistance. All those prill are covered, and you should be good to go. Factors affecting water resistance. Exposure time is, of course, big. We're talking about that right now. How long are you going to be sitting in that water? But then you also get into hydrostatic pressure. So is that just foam water? Is there pressure behind that water? Is it kind of like a streamer? Is there something that'll definitely affect it, washing away your product, things like that? Packaging, if you're going to use let's say packaged ANFO or liners, things like that, that's quite doable, but you want to make sure your packaging is stout. And if you develop a hole and allow a way for water to be introduced to that powder column, then you might run into problems. Water resistance can be as short as be a real short time. Like I said, ANFO will break down quickly to years. ANFO breaks down in minutes. Some emulsions can last for months, and I've seen shots with 50-50 for some unknown reason, whether there's a K order or something breaks down below and you can't get the coal out beneath the cast where you've had to sit for months. And that time you're worried about, your detonation system. You have to test it all the time. But I haven't seen a problem where you can get through that shop pretty easily. You don't get too scared about the product in there. All right, oxygen balance. So if there's just enough oxygen to convert all carbon to carbon dioxide and all hydrogen to water, then you have what you consider oxygen balance. It's that simple. Not achieving oxygen balance could result in a variation in energy output as well as fumes. So basically, too much oxygen or underfueled can create more NOx because you have excess oxygen there that's going to go into NOx, and then not enough oxygen, overfueled, you're going to go more towards the carbon monoxide. Now, having said that, if it's that simple to just, if you want to totally eliminate that orange cloud, just overfuel everything. Well, it's not that simple. There's other contributing factors there, but you're still at overfueled. You're bringing in carbon monoxide. So if you want to get into your fumes, NOx and carbon monoxide are your toxic ones. I mean, every blast you'll have carbon dioxide or steam and things like that are not toxic. But once you start getting the NOx and carbon monoxide, then you're starting to get those toxic fumes. You don't want either one. But on a whole, though, the industry seems to tend more towards overfueling. The reason for that, you do eliminate the potential for NOx. Like I said, it's just not that easy. But if you go 1% overfuel versus 1% underfuel, your energy is on an underfuel is going to be way less than if you slightly overfuel. So you want to weigh more on your overfueling, or tend to lean that way. Basically with that, I run through that pretty quick, but I am open to questions at this time.
Again, if anyone has any questions, they can raise their hand and we can unmute their microphone, or you can also write your questions in the question application of the menu. Okay, it looks like we don't have any questions. Thank you very much, Tony.
All right, thank you.
Next up is Ron Eastman. And Ron comes from NX USA, and he'll be doing a geology rock mechanics presentation. Ron, hopefully we have you still.
Oh.
There we are. We've got you.
My headphones quit working. I did have a question for Tony.
Ron, it does sound like your microphone's a little low again.
Yeah, my headphones quit working for some reason. So I don't know if I should call him or what. Take a quick break.
Yeah, let's do that. Let's take a quick break. And Ron, if you want to call in, and we'll try it here within about 5 minutes.
Okay.
Okay, sounds good. Thanks. We'll be back here in about 9:46, 9:47.
You got me, Rio? Oh, great.
I do. Probably mute your computer though.
Okay.
That's
I don't know
much
what
better.
happened to my headphones. Does this sound all right?
Yep. Sounds
Okay.
good.
We'll roll with this then.
Okay.
Yeah, my headphones were doing good, and then all of a sudden they weren't. You see my screen too?
I do. I see it.
Okay. A lot of what I'm going to cover, well, some of what I'm going to cover is kind of a little bit of what Tony covered in my next one, but
Okay.
it's a little different. So what time are we rejoining?
In about 2 minutes.
Okay.
So I said about 9:46.
We going to have a break in between mine, or do you want me to go the full 2 in a row?
I was gonna do Tony, then you without a break. So let's do yours and let's take another 5-minute break after this first presentation.
Okay.
Just
I don't know what happened to the headphones. I wonder if I should try them again.
No, it's all good. We'll maybe try it later.
Okay.
Hey Ron,
What's that? What's that noise?
I think your computer needs to be muted. Okay.
Is that better?
Yep, that's better.
Okay. I don't know what happened there.
Okay.
Okay, let's go ahead and get started again. We're going to try this again with Ron Eastman from NX USA. He's going to do a presentation on geology, rock mechanics.
Hey, everybody. Tony, if you're still on, I did have one quick question for you on yours.
I'm still
Not
here.
there no more?
Yeah,
Oh,
no,
okay. Hey, you talked about the density of krill and how, after several transportations or whatever, heat cycles, it can break down and change. Do you guys pay much attention to the density of your fuel oil?
I'll be 100% honest with you. We know what it is, but me personally, I've never really, because we do use used oil, and we know the density of that as it comes in, and we do use, right now we use some dyed diesel in some applications and regular diesel in other, but so we know it's out there. Yeah, that's a good number to know.
Yeah, I just didn't know if you paid attention to it, and if you did, what kind of ranges that you saw based on additives and other stuff they put in it.
Right, and that's the thing with the fuel, the used oil that we use in some locations, the number's there. I know what it is. I just don't have it for you right now. So, but we do make sure we know that. It's just I can't give you a range.
Okay, that's fine, buddy. I was just curious.
Yeah.
Okay,
No,
everybody.
good question.
I'm Ron East. Yeah, I'm Ron Eastman. Kind of with Tony. I've been in the industry for 20 some years. I do want to put a little disclaimer out there before I start. I did not write these presentations, and I'm not a geologist or a physicist, so it's my little disclaimer. So those of you that know me know that's true. So anyway, we'll get started with geology and rock mechanics. Somewhat boring stuff, but stuff that as a blaster you should know. So basically, the rocks are classified into three general types. You have your igneous rocks, you have sedimentary rocks, and you have, oh, holy cow, you have your metamorphic rocks. So almost all rocks start as igneous rocks with the exception of limestone and coal. Limestone's formed more based off of chemically, and coal is more organic. So igneous rocks are formed two different ways, intrusively and extrusively. So intrusive formed igneous rocks are from magma deep below the Earth's, the crust surface, the crust of the Earth. So it cools very, very slowly. Extrusive igneous rocks are formed from lava. So once that lava hits the surface, they cool very quickly. So you get two different types there. Sedimentary rocks are reassembled vestiges of eroded igneous rocks for the most part. So limestone can be formed chemically from the accumulation of dead organisms, or it can be precipitated from water. Metamorphic rocks are igneous or sedimentary rocks that have been altered through heat and pressure to change their crystal structure and sometimes composition. So everything basically starts from igneous. So why do we care about geology? It's the core of our business. It can define our blast and its performance, and everything we do is centralized around geology, from the rock type to the joints and structural geology. So igneous rocks, as you saw before, we have three examples up here, but granite is predominantly formed in igneous intrusions. Intrusions usually cool slower, allowing large crystals to form. So you can see the larger crystals in the granite. Rhyolite is an extrusive igneous rock with a high silica content, usually greater than about 69%. If it hasn't already cooled in the subsurface when it erupts, it will cool quickly after the eruption, leading to finer crystals. So you got a little finer crystals in the rhyolite. Basalt is usually an extrusive igneous rock. It is fine-grained and composed of mainly plagioclase and pyroxene minerals. So, for example, Hawaii is made of extrusive basalt, the whole island. Basalt can sometimes be intrusive as well, forming dikes or sills, but igneous rocks have tightly interlocking crystals, making them harder to blast. Sedimentary rocks, which is pretty much, if you're in the coal mining business, pretty much all you deal with for the most part. Very soft. They're classified mainly by grain size. Sandstone, for example, consists of grains cemented together by a matrix. Grain sizes can range from 1/16 of a millimeter to 2 millimeters. And limestone is composed primarily of calcium carbonate. Usually it forms in shallow marine environments and is essentially the culmination of biodetritus. Mudstone is composed of fine-grained particles of silt and clay size, synonymous with clay stones as siltstones. Grains are usually less than 0.06 millimeters. Shale is a hard and fizzle mudstone. Sedimentary rocks are usually relatively soft and have bedding planes, making them a little easier to blast. But for those of you that do blast in the basin, everybody says, oh, it's just dirt. But as everybody knows, it isn't as easy to shoot as, some hero rock in other places when you get into metal and non-metal. metamorphic rocks. Gneiss is a metamorphous granite. Quartzite is a metamorphous sandstone. And mica schist is a metamorphous mudstone. So basically, metamorphic rocks all pretty much come from igneous rocks as they erode or whatever, and then they're formed under pressure, great pressure and heat, and things like that. So note the crystals are more interlocked in metamorphic rocks with less matrix than their parent rocks. This can make them much more difficult to blast. So along with geology, you have faults. I know in the basin we've all seen faults. There's 4 major fault types. The first one on the top left here is a normal fault. One side slides down from the other due to tension. You can see by the darker arrows here, that's where your pressure is coming from on each of the pictures. A reverse fault is usually a steep angle formed when 2 sides are pushed together against one another. A thrust is like the reverse fault, but it has a much shallower angle, as you can see. And then your strike slip is basically pressure's pushing this way and pressure's going that way. The 2 sides slide against each other along the strike of the fault. So I don't know, I was in Utah or Nevada last week, and it was kind of interesting. I drove down along Lake Mead on the west side, and I didn't take these pictures, but it was interesting to see some of the interesting geology that was down there. So I've been working on this, studying this presentation a little bit, I've kind of noticed a lot more geology as I drive around. It is kind of interesting. So these top photos are basically some normal faults, these top 2. Your bottom left, where you can see it right here, is a thrust fault. And then the bottom right is a strike slip or transverse fault. You can kind of see how this material is going that way and this material is moving this way. You also have folds due to a lot of heat and pressure. There's 3 types of folds that are shown here. The first one on the top is an anticline. It's a linear strata, normally dip away from the axial center. It's the oldest strata, with the oldest strata in the center, irrespective of orientation. You got a syncline fold, which is linear. Strata normally dip toward the actual center, and the youngest strata in the center, irrespective of orientation. You have a monocline, which is a linear strata dip in one direction between horizontal layers on each side. And then there's numbers of other ones. There's an antiform, a synform, dome, basin, chevrons, recumbents, slump folds, parasitic folds, which have short wavelength folds formed within a larger wavelength fold structure. So a lot of different interesting folds. And you can see some examples of some here. Folds are just that, they're folds. They can range in size from being very microscopic to mountain sized, as this one over here on the left is. They occur from deformation in the rock mass, from tectonic movement, igneous intrusions, slumping, etc. Folds commonly form compressive stresses in the rock mass. The bottom right one's pretty interesting. They're all kind of interesting, neat pictures. And then you have structural geology as far as joints. Joints are the brittle fracturing of rock masses due to tensile stresses during cooling, or they are formed along bedding planes. They're important to us because they are the initial defining boundaries for fragmentation when present. And talking about fragmentation, I mean, each one of these forms of geology in these pictures would be very difficult to blast. So when you start talking fragmentation versus like displacement, you can see in some of these pictures, there's obviously some fragmentation there, but there's no displacement. So when you're talking about blasting, yeah, a shot can shoot well, but does it have displacement? The fragmentation can be great, but is there really any displacement there? So one way to look at it is if you were like to take a skid steer loader and I put a big pile of bricks out there, okay? There's definitely fragmentation. All the bricks are the same size. It'd be relatively easy to scoop those into the bucket because there is displacement. Now, if I took the same amount of bricks and stacked them all nice and neat, we still got the same amount of fragmentation, but without that displacement, that one would be much more difficult to dig. We also have types of failures in slope stability. So I know Rio and anybody that's driven between Buffalo and Sheridan on I-90 have seen plenty of those bowl-shaped failures. You can see them along the interstate there. Bowl-shaped failures are usually associated with soils. So that's why you see a lot of that up there around Sheridan. Planter failures are ones in which a block of material slides down a plane of weakness. Can be rock, can be soil. I mean, I've seen those in the basin. I've actually drilled a row of holes when I was first getting trained to run a drill, and we backed up and started a second row of holes, and about the time we got the second hole in the second row, 3/4 of the first row was gone. Just planter wedge and down it went. Wedge failures are caused by the intersection of two major set joints. Joint sets, these often happen in rock. So I'm not sure, but I'm thinking that big failure that happened in Bingham Canyon was probably a failure along a wedge failure. And toppling occurs when the bedding planes are turned upright or the material is excavated at too steep of a face angle. So an example here of slope stability, in this scenario, there is a weakness plane behind and at a different angle to the face. So gravity acts to pull that rock down right here. And the toe resists the horizontal movement. So you have some resistance at the toe. If the forces at the toe are strong enough down here, the slope will remain stable. If the toe is undercut, got overdig or something like that, now your toe resistance has been reduced. So now it's good potential that this slope will fail at this point. If there is material added or left at the toe, this will provide greater resistance to the horizontal forces, and the slope has a greater chance to remain stable, as long as you keep that toe resistance there. Now, water, that's a wholly different thing. I mean, Tony talked about it a little bit when you're watching high walls, and water is huge. You know, you get freeze-thaw cycles, which I'll talk about in a minute, but water's big. So if there is water introduced to the system, it will act in a couple different ways. First, it will accumulate in any joints or cracks and act as a lubricant. If the water is under pressure, it can force the two blocks apart, allowing them to easily slide past one another. If it is a cold environment and the water continues to freeze and thaw, it can move the block through a phenomenon called frost wedging. As ice freezes, it expands and pushes the blocks apart. But then it thaws, but the block might remain separated further than they were prior to freezing. So then the water can fill the cracks once again, freeze, pushing the blocks even further apart, and so on until eventually you will have a failure. And we get a lot of these freeze cycles around here in Wyoming, and I know there is in a lot of other places in the U.S. Water in the springtime around here is one of our biggest issues with high walls, as well as, you know, just flat getting around. But water's an interesting thing to pay attention to with high wall stability. So back, kind of like a little example here of slope stability with some grains of sand or rock. But when they're dry, they're packed closely together, and gravity and weight are keeping them in contact. Friction and or cohesion are keeping them from sliding past one another. When water is introduced, especially under pressure, it will force the particles apart so they are no longer in contact with each other, and friction and cohesive forces are reduced to nothing, so the grain can move by each other easily. like I said, water is one of the biggest influential factors in slope failures. Now we'll get into a little bit of rock mechanics. So there are ways that they go through several different tests here to figure out just how hard a rock is. So there's three types of stress in rock mechanics. You have the compression, which is like trying to squeeze the rock. You have tensile, which is trying to tear it apart. And you have a shear, which is kind of putting pressure on the top and then opposite direction on the bottom. So compression is like squeezing. Tensional stress is pulling it apart, and shear stress is moving one side relative to the other. Stress is simply the pressure acting on a rock. It is a force divided by the area. I don't expect you to know the formulas. So in rock mechanics, strain is this symbol up here. Strain is the ratio of deformation to the original amount and is therefore dimensionless. It is denoted by E. There are three types of stress in rock mechanics. So strain is a result of stress. So different rocks act differently when stress is applied to them. So strain is the amount that the rock deforms based on the amount of stress applied. This rock can either act elastically or plastically. If the stress is small enough and the rock acts in an elastic manner, it will return to its original shape after the stress is removed. If the rock is deformed plastically, then it will remain deformed after the stress is removed, as in the example shown. So basically this calculation is just, you got your length, which is the bottom, and you got this distance here of how much strain this rock has absorbed. You put this into the formula and you get your percentages of strain here. So Young's modulus is the ability of a material to withstand changes in length when under axial compression or tension. Is the slope of the elastic region of the stress strain curve. As you apply a force to a core sample, it will deform. While it is in its elastic region, when you remove the force, it will rebound to its original shape. The slope of the line for the amount of stress applied to the amount of deformation obtained is basically Young's modulus. So on the left is a unilateral axial compression test. So a core of the rock, usually there's a defined length to diameter ratio, is loaded into a hydraulic press, and the load is applied while the deformation is measured. The center is a Brazilian test. This measures the tensile strength of the rock. A disc of rock is compressed on its sides. This induces tensile stress perpendicular to the load. Shear strength testing is shown on the right, and a sample is loaded into the test apparatus and a shear force is applied to it. So why do all these tests? Basically, it gives you general values for different rock masses. The tensile strength of a rock is usually about 1/10 of its compression strength. And it's important to point this out because the tensile stress is created by reflecting shock waves from explosives. You know, this is covered, we'll cover this in the next one. But it's, so you can see, you know, mudstones, sandstones, most of your sedimentary rock and all that is in your weak to very weak to moderately weak stuff. You get more into metal, non-metal, quarries, things like that, you're going to start getting into your strong, very strong and extremely strong rock. So just a little thing here. Harder rocks are usually igneous and contain some metamorphics, and softer rocks are usually sedimentary and also contain some metamorphics. But metal mines, non-metal mines are usually a harder rock. Coal mines are usually soft rock. Harder rocks should typically, rule of thumb, should be timed a little faster. Softer rocks should typically be timed a little slower. So faster timing usually promotes fragmentation, and slower timing usually promotes movement. So just a simple rule of thumb, you're looking at approximately 0.5 millisecond to 1.5 milliseconds per foot of burden and spacing for fragmentation. and 4.5 to 12 milliseconds a foot per throw. Timing that is too slow, though, can induce post-blast fumes or cutoffs, and timing that is too fast can bind the shot up and cause additional backbreak. So just rules of thumb, but I think you've all seen timing that's too fast can cause a lot of extra backbreak, and too slow is not always necessarily good too. So just rules of thumb, but you have to kind of figure out what works the best in your environment and your geology. I mean, for most of us that mine here in the basin, coal is coal. I mean, it does have some planes and some grain to it. Depending on which way your pit is moving, you kind of pay attention to that. But once you kind of dial it in from a timing aspect and a loading aspect, it's pretty consistent. The material that we mine here in the basin is, for the overburden, is relatively soft, very little rock in it. It doesn't mean that it makes it easier to shoot, but it is softer for sure. And you get into metal, non-metal mines, and depending on your mine, you could have all kinds of different geology in just one pit alone. Some of them I've been to are relatively consistent on geology, and some are just all over the place. And for blasters that may be on here that, you know, work for an explosive company that have to travel from, you know, quarry to quarry to quarry to shoot in different places all the time, need to be a little bit of aware of what their geology is as well, at each different operation, because each one might be, you know, a little bit different than the one they did yesterday. So it is important to pay attention to your geology, what you're actually trying to shoot, how strong is the rock, how dense the rock is, those kind of things. So with that, that's about, like I said, I'm not a geologist, but that's about all I have on geology. Got any questions?
Okay, we'll open it up for questions now. Again, you can raise your hand, or you can write your question in the question application in the menu. Okay, Ron, it doesn't look like we have any questions. Did you want to continue, or are we going to take a break?
Whatever you want to do. I can move right into the next one, or we can take a break.
Let's go ahead. This is Rio. Let's go ahead and take a 10-minute break.
Okay, we'll take a 10-minute break. We'll be right back.
Okay, we'll be back.
Real, you there? You there, Real?
Yes, I'm here.
Oh, okay. Thought maybe my
No, sorry.
things would
Stepped out of
scrap
off.
again.
Yeah, we'll get going here in about 3 minutes.
Okay. I just seen something from you that said, let me know when you're ready.
Hey, Ron, are you there?
I am, buddy.
Hey, yeah, all of our oils I've been looking here, we're kind of right in the same, whether it's used oil or diesel, they're right around the same weight per gallon. But the one thing that I should have added is when we are using that used oil, what we run into is you get some trash that comes back to you and you plug filters. So you have to really be careful with that. That's our biggest concern out there. So that's, I should expounded on that. You may not be pumping at the rate you think. You need to always be on track with that with used oil. But other than that, yeah, we're pretty close with used oil and all of our diesel. So.
Okay. Yeah, I didn't know how much it fluctuated with additives, winter blends versus summer blends and all that kind of stuff. I didn't know if that density range was somewhat great or if it was pretty similar.
Yeah, do you see a big change? I know you go around the region a lot more than I do. I'm typically in the Powder River Basin, but do you see a big change in density?
Well, I haven't measured a whole lot of them, but that's why I
Okay.
was just wondering if you have.
Yeah, no, like I said, our biggest thing is our, when you're looking at our filters and our Y strainers getting plugged up with that used oil, they say they bring back clean stuff, but it's not. It's horrible.
Hey, Tony and Ron, I was going to have Keith start the next session.
Okay.
But you guys mind taking a second and explaining when you say used oil, what that means? I don't know how many other regions use used or recycled oil.
Yeah, I can do that.
Okay, go ahead, Keith.
Okay, we're going to have Ron sorry, with NAX, detonation shock physics rock breakage. Ron, I've already shared the screen to the attendees.
Okay, am I there?
You are.
Okay, perfect. Okay, Tony, you don't have to respond, but a lot of what I'm going to talk about here as far as detonation, shock physics, and rock breakage, Tony covered a little bit of it in his presentation. Maybe I'll go into a little more detail, maybe I won't, but it shouldn't be too repetitive for the most part. So just a little bit of a warning there to you. So to start off, Tony kind of started off the same way here, detonation. It's a sudden release of energy and reaction products at a high pressure and temperature by a rapid chemical reaction. Tony was right there with the same thing. If the chemical reaction travels through the material or the explosive faster than the speed of sound of that material, then it is a detonation. If it travels slower than the speed of sound of that material, then it is a deflagration. The detonation transfer its energy to the surroundings in the form of a shock wave. So you can see the shock waves in each one of these pictures. So anatomy of detonation, just going to go into it in a little bit more detail maybe. This is basically just a picture of some PETN detonated in plexiglass. And we're just going to overlay a steel frame or a graph at the bottom, the hypothetical plot of pressure versus distance along the charge. So basically you have your undetonated explosives in this kind of green, dark green shaded area. Right here, the leading edge of this little red thing right here, that's your detonation front. Okay, leading edge is the detonation front. This is how wide that detonation front is. And right at the leading edge, there's an instantaneous increase in pressure. The reaction zone, which is this whole entire red section right in here, that's where everything's happening. That's where all your molecules or atoms are just getting ripped apart. And heat and energy are starting to be released at that point. It's an instantaneous increase in pressure. Your shock wave, you can see your shock wave coming out of that from all that heat and pressure. And then you have your CJ pressure at the back of the reaction zone. So on the back side of this reaction zone is your CJ pressure. And the detonation creates a shock wave in the surrounding material that moves outward. And then you have borehole expansion starting to begin right in here. And then you have gas expansion. And so eventually the material begins to fail and the gases continue to expand. So to look into it a little bit deeper, the molecules of the explosives are broken apart in the reaction zone. So this is your reaction zone, once again, this red spot here. And the atoms begin to recombine and expand back here in the reaction product expansion. That's where you're getting your gas. The shock energy is the partition attributed to the detonation velocity and the thickness of the reaction zone. And the heave energy is the partition attributed to the expansion of the reaction products. So the leading edge of the detonation is supersonic right here as it moves through the undetonated explosives. And the reaction zone is subsonic because the pressure and density is so high. The CJ plane is where the pressure and density drop off enough for it to be traveling at supersonic speed again. And this allows the detonation to continue traveling forward. So a little video here. Don't need any sound for this one. You can see as it goes, you can see the shock wave starting to come out. See the gases start to form behind it. So the width of the reaction zone is proportional to the detonation velocity. So for a high VOD, the reaction zone may be less than a millimeter. For lower VODs now, the reaction zone may be 10 times that or more. So you're getting, obviously this is a bigger reaction zone, so the reaction is happening at a much slower rate than it is when it's tight like this, when it's narrow. And you also, the thinner the reaction zone is compared to the diameter of the explosives, the closer the VOD will reach its ideal maximum. At a constant diameter, the edge losses increase as the reaction zone width increases. This is a reason why lower VOD explosives need a larger diameter to detonate, or why higher VOD explosives have smaller critical diameters. So the width of the, as I said, the width of the reaction zone is proportional to the detonation velocity. The thinner the reaction zone is when compared to the diameter of the explosive, the closer the VOD will reach its ideal maximum. At a constant diameter, the edge losses increase as the reaction zone width increases. This is why lower VOD explosives need a larger diameter to detonate, or why higher VODs have smaller critical diameters. So the tighter this reaction zone is, the better the VOD, the higher the velocity. So in this diagram, we're basically just demonstrating a detonation and an explosive with a progressively reducing diameter. There is a point in which the edge losses are too great and the detonation will cease to continue. So right here, you have a really good, tight, very little edge loss. As the diameter gets smaller, the reaction zone gets bigger. There becomes more and more edge loss until it reaches a certain diameter, which is critical diameter is reached, then the detonation will stop. Other major effects on critical diameter are caused by confinement, density, particle size, initial temperature, additives. There's other things that can affect a critical diameter, but it will eventually hit a critical diameter and cease to keep moving forward. So as far as confinement is concerned, when that reaction, the products expand, the pressure and temperature reduces. So if you have low confinement, this pressure and temperature gets reduced. And confinement slows the expansion of the reaction products. So confinement also reduces the amount of loss in terms of pressure and temperature behind the detonation front, thereby increasing the reaction rates and helping to sustain the detonation. So a little bit better confinement, you got higher temperature, higher pressure, and a better reaction zone than you do in a low confinement situation. And Tony touched on this a little bit too, but hotspot theory, sometimes even a large diameter isn't enough to maintain a good solid detonation. So you may need to introduce localized hotspots to increase the sensitivity of the explosive. So that could be bubbles, could be gassing, could be prill, all can be hotspots. But basically how it works is the shock wave moves in from the left. As it impacts the air bubbles, they begin to collapse. The side of the bubble is inverted and pushed into the opposite side. And as this happens, the air is compressed so much that an extreme amount of heat is released and a shock wave is produced, both adding to the original. This allows the shock wave to progress through the material. So just a little idea here, critical density and molecular explosives, the detonation velocity is a linear relationship to the explosive density. So critical density for ammonia nitrate emulsion explosive is dictated by the sensitivity of the emulsion, which is proportional to the number of available hotspots. So there's different ways to form these hotspots. Like I mentioned, you can do it chemically through gassing, and I'll cover this a little bit more in sensitization later. Or you can use microballoons, could be plastic, glass, resin. But you can see here the hotspots that are created in this one here versus this emulsion over here that doesn't have a whole lot of hotspots in it. So basically, you talk energy partitioning, which Tony touched on a little bit too. Total energy of a detonation is partitioned into two. The initial increase in pressure that is associated with the shock wave is the shock component. That's your shock energy, the brisance. And the expansion of the reaction products and the pressure associated is the gas or heave component. So total energy equals shock energy plus gas energy. So you have your shock out here, your brisance, you have your gas and your heave coming behind that inside here. The shock component is responsible for spalling or cracking. Tony touched on this, and the fragmentation. So your shock energy is providing the cracks. And then the heave component opens cracks further and moves the material, gives you that throw or that heave, that gas energy does. That's why most of these heavy ampo products that we run, you want a pretty good combination depending on what you're blasting at both shock and heave. And I don't know, can you play this one, Keith?
We
Or
can.
do I
Let
need
me
to
just,
play it?
yeah, let me
Okay.
let me share it now. One sec.
Okay. For those of you that have seen this, might be a little boring to watch it again, but it's an old video, and it's kind of interesting to watch if you haven't seen it, to what happens with how explosions react underneath water, especially when a surface is placed near them.
This diagram shows the action of a small
Is it
scale
playing, Keith,
underwater
or?
explosion. At the instant of detonation,
It is.
the enormous initial pressure,
Okay, I
estimated
can't
to
see
be
it
in the
then.
order of 100,000 atmospheres, is produced. This pressure dispatches a shock wave and imparts a large momentum to the water. Because of the large momentum, a gas globe, produced by products of the explosion, expands radially outward. It travels beyond the point at which its internal pressure equals the hydrostatic head of the surrounding water. Eventually, however, the hydrostatic pressure brings the expansion to a halt. And since the interior of the globe is at a low pressure, a contraction is started. At the point of collapse, another shock wave will be sent on its way, and the cycle of expansion and contraction will be repeated until all the energy of motion is dissipated. Here, a number 8 electric blasting cap is exploded 12 inches below the water surface. The total depth of the water is 6 feet. Note that each succeeding pulse decreases in amplitude and duration. The depth below the surface is increased to 24 inches. The object at the extreme right is the illuminating lamp. You may observe a cavitational fog coming from the lamp. The same explosion at 36 inches below the surface. The gas globe formed in this explosion will reach a maximum diameter of 11 inches. The time required for the first pulsation was 24 thousandths of a second. The charge is placed 36 inches below the water's surface, 30 inches from the back wall, and 24 inches from the side wall. The rigid surface of the nearby wall attracts the gas globe. The charge is moved to 18 inches from the side wall. Note the motion of the globe towards the side wall. The same charge 12 inches from the side wall. It will be noted that the gas globe starts its movement toward the side wall only after the completion of the first pulse. The charge is now 6 inches from the side wall. The vibrations of the lucite lamp face are caught in slow motion. Again, you may observe a cavitational fog which appears to come from the lamp face. The charge is now moved to within 3 inches of the wall. Observe how the gas globe beats upon the wall. The number 8 cap in contact with the side wall. The gas globe formed against the wall has less than half the volume of the globe formed away from the wall. These sequences have shown that the second and succeeding pulses moved toward the side wall. Later pictures will show that the gas globe moves toward any rigid surface. Here, a 4-foot square, flat-bottomed float drawing 1 inch of water serves as a boat. A number 8 detonator cap is placed 12 inches under the boat. The globe moves slowly downward, away from the boat. We have previously seen, under similar conditions, but without the boat, that the gas globe also moved downward. The charge is placed 6 inches under the boat. The globe moves toward the boat. This parallels the action previously observed when the charge was placed 6 inches from a vertical wall. In contact with the boat, the charge is the dark object lying horizontally just above the center of the picture. Here, as in contact with the vertical wall, the gas globe has less than half the volume of the globe formed away from the boat. The water is 36 inches deep. The charge is in contact with the bottom. Midway between the bottom and the water surface, the gas globe moves toward the bottom. The cap placed 3 inches under the surface. Observe that the gas globe travels 33 inches to the bottom. 1 inch under the water surface and 35 inches above the bottom. In shallow water, the bottom of a boat and the channel bottom present relatively rigid adjacent surfaces. The cap is 23 inches below the boat and 10 1/2 inches above the bottom. The gas globe is attracted by the nearest and most rigid surface. A charge twice as heavy is fired with the same setup. A still larger charge, 1/2 ounce of tetrol. This is studied by a number 8 cap midway between 2 vertical steel plates, 12 inches square, 1/2 inch thick, 18 inches apart. When the plates are 12 inches apart, the globe divides and attacks both plates. Firing between the plates 6 inches apart. Note the vibration of the plates in opposite phase. These photographs have been presented as studies of the very rapid action which takes place in underwater explosions. While the explosive actions shown here were violent, it must be remembered that they have been explosions of a very small scale. The relationship between the action of the small charges used in these experiments and the explosions of mines and torpedoes is not known. However, it is hoped that studies such as these will aid our understanding of the explosive action on the hull of a ship.
Okay, Ron, I have shared the screen back with you.
Okay, thanks. So kind of an interesting video. I mean, so basically the energy partition measurements are performed underwater and calculated by measuring the pressure of the initial shock wave and then relating that to the attenuation of the subsequent shock waves and bubble expansion. So the globe, the initial detonation goes, and then the pressure from the water allows it to contract, and then it's got enough energy to just kind of keep rebounding until the pressure over time equalizes itself. So I think basically what that video is kind of showing and how it relates to us is kind of how a tensile wave is formed as well. So basically crack formation and how a borehole actually shoots is as the shock wave propagates outward, which would be this red circle, the borehole will swell. Whoops. The borehole will swell. You kind of see it start to swell in here. And the tangential stresses work on the rock to form fractures, okay? At about 1 hole diameter away from the borehole wall, the stress starts some large radial fractures. These cracks move outward and inward. Usually around 5 major radial cracks are formed from each borehole. And there is an area around the borehole in which the pressure from the shock wave far exceeds the compressive strength of the rock, forming a zone of crushed rock. So you're just going to get some pulverized material in here, and you're going to get your cracks that start to form out here, and then your detonaceous gases start wedging into those fractures and cracks to start the process of the heave. So back to the tensile wave. The detonation of the product in the borehole gives rise to an initial shock wave that quickly attenuates into a stress wave that propagates outward. The stress wave reflects and refracts off of boundaries like a free face, similar to what you saw in the video. The reflected stress wave induces more strain on the cracks that are parallel to it. These cracks will have a greater propagation velocity over other immediate cracks and therefore travel ahead. The stress wave will reflect and refract off of boundaries of varying densities, free faces, joints, bedding planes, pre-split cracks, etc., causing more tensile strain. So the compression wave is trying to squeeze the rock, and once it hits that free face, that tensile wave comes back in a tensile form now, trying to rip the rock apart. And then the gas works into those cracks and starts to do its thing with the heave and the throw. So when firing multiple holes, notice that the breakout angle for each hole as it fires, and cracks do tend to form across unfired blast holes. Those cracks do tend to go down your row. So, and with that, guys, that covers detonation, a little bit on shock physics, and a little bit on rock breakage. Anybody got any questions?
Once again, you can raise your hand in the application, or you can also write your question through the system as well.
Hey Ron, I do have a question. This is Rio. I showed the video of blasting or the blasting cap underwater. Is there any relation to blasting in overburden or coal? Does it collapse like that?
You mean as far as what we saw in the video and what it does when we shoot?
Yes.
Yeah, I think so. I think what we're actually seeing is that tensile strength. So as that explosion happens in the video, it would happen, but then it would always draw towards the harder material. So I think that's exactly what happens when we blast, is you shoot a borehole, and as soon as it reaches the free face or the free face created by the hole in front of it, it reflects in that tensile wave and wants to come back to that partition, which is the bench. This is kind of the way I understand that. If somebody's got a little better explanation, please jump in. Does that answer your question, Real, I guess?
Yes, it does.
Looks like Brad Brown has a question.
Okay, go ahead, Brad. Just remember, Brad, I'm not a physicist.
There, now they can hear me. I like what you got there. I like putting the, as much as I hate geology, frankly, I like putting the two together there. And Rio's bit about the effects that we see in this real laminated material, this sedimentary formation. The other things I see is you can lose a lot of gas in a hurry out at the face if you're not careful. You can bleed gas energy back in through weak strata back into adjacent holes, and we see a lot of that. Particularly when you think about Tony talking about fumes and things like that, you can have a lot of effects going on. And your other bit about some of the stacking of bricks, some of the harder formations, whether it's column or basalts or good hard stuff there in the Midwest and other places. You can break it, you can shock it, but if you don't move it with that gas energy, you got a real problem there. You can also bleed out a lot of gas energy through some of that structure and just never get the energy through a crack, through a formation fault or whatever, and into the next chunk. Just a huge number of things that can go on the shots that the blasters have to be aware of. It calls for good read of the rocks and information from the drillers, and then applying the right products and the right distribution to make it all work. It's a huge topic,
Yep.
but really well done. Thank you.
Thank you. Yeah, but people always think of fragmentation, but you really got to think displacement as well. I've been in a lot of places where the fragmentation looks good. There's good fragmentation, but there's not a lot of displacement. So the shovels or the excavators or whatever actually do struggle. So you kind of got to think of both.
Okay, any other questions or comments? All right, Ron, I think we're going to go on to the next section, sensitization stemming.
Okay. This one's a little bit more basic, guys. It's going to cover a little bit more on sensitization. And then another thing I just want to talk a little bit about too is stemming. I think stemming is really important and can sometimes be overlooked. So basically, let's talk a little bit about emulsions. Tony's hit on it a little bit already. In order for most ammonium nitrate emulsions to detonate on their own, they need to be sensitized. So any non-sensitized emulsion needs to become sensitized somehow. So they become sensitized by adding the release of high temperature and energy in localized spaces called hotspots. And I know we talked about hotspots a couple times. Tony's done it. I've done it already once. But hotspots come in the form of small voids created in the emulsion or the blend. So as we know, an unsensitized emulsion will not shoot all by itself. So blends of AMPO and emulsion with an unsensitized emulsion will usually be detonate full order up to around 45% emulsion, 55% AMPO. With an unsensitized emulsion, you don't want to be getting much over, I'd say 45, 50%. You have a chance of that emulsion not shooting, deflagrating. 50% blends are on the edge of sensitivity if they are using an unsensitized emulsion. So pay attention if you are using an unsensitized emulsion. I think most blasters are aware of this. But once that blend goes over 40% emulsion, the emulsion should be sensitized to help ensure full order of detonation. So how do we do that? Well, once again, I already explained the hotspot theory, but you basically want to add some hotspots into that unsensitized emulsion. So I explained how this theory works once. The shock wave moves in from the left. It impacts the air bubbles. They begin to collapse. The side of the bubble is inverted and pushed into the opposite side. And as this happens, the air is compressed so much that an extreme amount of heat is released and a shock wave is produced, both adding to the original, and this allows that shock wave to move through the material. So hotspots, how are they formed? Well, different ways you can basically sensitize emulsion. You can do it chemically by gassing. I've definitely seen that. I don't know if it's a real huge thing. I know it's not around here as much anymore. but I have gone to places in my travels where they are chemically gassing their emulsion. You can do it physically by adding your microballoons, whether they're plastic or glass or some kind of resin, or you can do it with prill, as we talked about. You just, in an unsensitized emulsion, though, you don't want to get more than, much more than 45-50% emulsion, but you can. Prill does act as hot spots in an unsensitized emulsion. So in molecular explosives, the detonation velocity is a linear relationship to the explosive density. So critical density for ammonia nitrate-based emulsion explosives is dictated by the sensitivity of the emulsion, which is proportional to the number of available hotspots. So obviously, the more hotspots you have in it here, the more sensitive that product's going to be. The less hotspots, the less sensitive that product's going to be. Whoops. So as far as chemical sensitization, as far as gassing goes, chemical gassing occurs when an amount of sodium, for those of you who don't know, I guess, chemical gassing occurs when an amount of sodium nitrate is mixed with an acid. This reaction releases nitrogen gas that forms small bubbles within the emulsion. The bubbles are on the order of around 300 microns in size, and these bubbles are what act as the hot spots that produce the added heat and energy to the system. So instead of you're physically putting in your microballoons and things like that, we're doing it chemically. This slide is showing the volume that 100 pounds of emulsion will occupy when gassed to two different densities. So the diagram on the left shows the emulsion at about a 1.25 density, and the diagram on the right shows the emulsion at 1.1 density. The emulsion on the right occupies more volume because it's been gassed to a lower density. So to explain that a little bit more, so when you're loading with a gas product, if any of you are, this diagram shows what happens when an emulsion is loaded into a hole and gassed. So over time, that chemical reaction takes place, the bubbles will form and lower the density of the explosive, and the column will rise as a result. So if any of you have ever gassed before, you need to know about how much this column's going to rise. And it usually takes about 30 to 45 minutes, depending on a number of factors, but the explosive column will reach its final height, and the product should be loaded to accommodate gassing. So you need to know about what that column rise is going to be. Now, there is some issues with gassing as well due to hydrostatic head. As the depth increases, it tends to compress the bubbles more. So your product at the bottom of the hole will have bubbles, but they'll have a much smaller diameter than the bubbles near the surface. So this does not occur with physically sensitized emulsion products because the void is surrounded by a rigid structure that can resist the hydrostatic pressure. So when you're physically sensitizing emulsion with glass beads or plastic beads of that nature, those are much more rigid in structure and they can resist that hydrostatic pressure. But when gassing, you still have those bubbles in there, but you just got a much denser product in the bottom than you do in the top, as you can see by the curve here. And then by the diagram here, you got good gassing here, bubbles are getting smaller, bubbles are getting smaller. So an example of this is just showing how, due to hydrostatic pressure, the density will increase with the depth. So when gas emulsions are loaded, the operator will use what is called the density curve. It allows them to determine what the clump density at the surface will be to achieve an average in-hole density. So if you're putting in product with a 1.15 density, at the top, it's probably going to gas very nicely, maybe get you down to a 0.95 density. But down at the bottom, you're looking at, a much heavier product with much smaller bubbles and hot spots in it. That's about all I have on emulsion and sensitizing it. It's really pretty basic. I don't know if any of you guys have ever actually seen those little bubbles and little hot spots that come in glass or plastic, but they just look like dust. They are so fine. It's pretty interesting. But I know if you do put way too much of those in there, you can make the product way too sensitive and possibly even get it to cap sensitive, which we don't want to do, because now you're starting to interrupt that explosive train. So with no more on that, I'd like to move into stemming. Stemming, like I said, I think is overlooked to some examples. A lot of places you go, they use a crushed angular stone. That's probably ultimately your best material for stemming. It locks together very nice. Rounded stones don't have the same interlocking capability, but they're still not a bad stemming. And drill cuttings have a lot of fines in them. They lack the larger chips, which have the capability of locking in there tighter. That doesn't mean that drill cuttings can be used. I mean, here in the basin with this softer sedimentary rock, drill cuttings is predominantly used. We don't need to get the powder column as high as we need. There's a lot of places to break that rock at the top. In casting, you don't really want that energy being released at the top of the hole. You want it released out the face. So we have typically in a coal mine situation, you're going to have a much greater amount of stemming in the hole than you might in a metal, non-metal, or a quarry. I mean, almost every quarry and non-metal mine I've ever been to, it's predominantly some kind of crushed stone. And, your stemming size should be, rule of thumb, about a 20th and 1/10 or so of your hole diameter. And at all chances you can, run it through some kind of a grizzly or a screen to make sure that your size is consistent. So, like I said, with an angular gravel, you have very good interlocking of angular edges, which makes for very good stemming. A rounded gravel, or even if you could even put a sand down as a rounded gravel, you got many more slip planes in there. It's not going to lock quite as good as an angular. And once again, drill cuttings, fines don't provide good locking, but depending on the amount of stemming you're putting in the hole, as I mentioned before, drill cuttings can be just fine in a lot of places. If you're trying to bring a powder column up in a hard rock mine, I wouldn't recommend drill cuttings, and most places don't use them anyway. So how do you stem? I mean, there's a lot of different ways. I've seen all of these in my travels. I've seen stemming trucks. I've seen side dump loaders, skid steers, big and cold, because normally, like I said, we're stemming with drill cuttings. Easy to push them in, easy to smash them if they're frozen. I have actually seen conveyors, like similar to a stemming truck, on a bucket for small diameter holes. They could fill up and they could shoot the stemming out either side. That works well. These side dump loaders work extremely well. You have very little waste. If the operator, hits the bullseye, you got very little waste. Most of them have a grizzly right here on the end. It's an added grizzly to separate the larger chunks. They work really well. Stemming trucks are fantastic. You just run them up there to the gravel, get a loader, fill them up. They got the grizzly right on the top to separate out the larger material. Every pattern I've been on with the stemming truck, though, boy, they're fantastic. That prepare to get your shovel out and stem some, because hand shovel some holes, because a stemming truck, I haven't been on a pattern yet where a stemming truck was able to get to every single hole that needed to be stemmed. So, but they are fantastic, and trust me, when they go down, you feel it. So just different applications. I mean, depending on what you're doing. The side dump loaders work really nice if you are, pulling stemming out of a pile. So just different ways of doing things. So why do we stem? I mean, we obviously stem because we want confinement. So that's why picking your stemming is somewhat important. So you got this diagram basically is demonstrating the level of confinement for different stemming materials. So if you put no stemming in it, obviously we've probably all been in that situation before. We overloaded the hole, and rather than put a little bit of stemming in it and add a bunch of ammo to it, some of us may have made the decision not to stem it at all. But what happens is you're just getting an extreme amount of rifling. Nothing's going to happen down here where you want it to. drill cuttings in, like, say, a hard rock situation, yeah, you're going to get a little fragmentation down here, but you're also going to get some release of energy up here where you don't need it. And if you use a good angular stone and you got the right stem height, you should get very good work down here where you need it, and you should get a good amount of heave up here at the top without any ejections or rifling or any of that kind of stuff. Another thing on stemming that's very important is you got to take care to ensure that large rocks don't fall down the hole. These can cause cutoffs or wedge themselves in the hole, causing an unintentional air deck, which would reduce your amount of stemming, which could cause fly rock. You need to be careful when you're stemming with a bobcat or something like that, that you aren't digging too deep along the actual grade of the bench, picking up any kind of rocks that may be underneath that stemming pile. A lot of cases, I think it's very, very good if you can have somebody go with you to stem. A lot of cases, I'll take a shovel, just a round pointed shovel, and hold it over that collar, over that down line. Decreases the size of the hole a little bit, but it also helps any rocks hitting that down line. And it also makes the diameter of the hole, the space, a little smaller, so you can catch anything that's kind of big that's going down in there. You know, down lines now, you know, everybody says, you know, non-Ls are really tough, but I'll guarantee you non-Ls do break. The problem is you don't know it. And now with electronics, everybody says they're much more fragile. Yes, maybe they are, but they're also a tattletale. They're 100% accountability for electronics, so it is, you know, treat them with a little more care. Most people do. Most people don't really think about it when they're stemming with non-Ls very much, because they just don't know until something digs into it and finds that they had a misfire. So it's just really important to pay attention to taking care of the downlines no matter what they are. And this is just a little thing I threw in there. I don't know if any of you've seen this or have used this. I've used it several times. It's actually a very good scale depth of burial kind of rule of thumb to get you, if you're going to a new place or a new area and you kind of want to get a good idea of where you should be from a stemming standpoint as far as what you want your muck pile to look like, then this is a good little simple formula that you can use to kind of determine what your stem height should be. And I'll walk you through this real quick just so you can kind of see how it works. And maybe some of you might want to try it, might not, or at least check and see exactly where you're falling on this scale with what you're currently doing. But it's pretty simple. For this example, we're going to use a 10 5/8 hole. We've got a 55-foot deep hole. We're going to put 20 foot of stemming on it. We're using a 1.2 density product. So the formula is basically scale depth of burial equals your distance divided by the cube root of your weight. So we need to figure out what the top 10 diameters of the borehole are. So to get 10 diameters, you take 10 times the hole diameter, which is 10.625, and divide it by inches, 12, to get it into feet. That'll calculate out at 8.8 feet. And your distance of 20 feet is your stemming. And then you only want half of this. So that cut half of 8.8 is 4.4 for a total distance of 24.4 feet. Okay. So then you calculate how many pounds you got per foot. Come up to 46.1. So 8.8 feet times 46.1 gives you 405 pounds. That's your weight. The weight is the total of these 10 diameters. So you put those numbers in the formula over here. So you got your distance, which is 24.4. Take your cube root of 405 and do the division, and you come up with 3.3. So on that scale that I showed you earlier, scale of distance burial will be a little bit on the high side of this diagram here at 3.3, and hopefully that would be your result. Would be just a nice good heave, a good breakage down in the bottom. And that's all I have on sensitization and stemming. Any questions?
Ron, we do have a couple questions. I'm going to call on one attendee, and I apologize if I mispronounce your last name. It's Dennis Wulzbacher, and I apologize if that's incorrect. But Dennis, I'm going to unmute your microphone.
Okay, yeah, this is Dennis Wilsbacher. You said my name pretty good. Concerning the previous, well, and part of this also, heave, we talk about the example of a stacked pile of bricks versus a loose pile of bricks and how easy it is for an excavator to load that. There's one other point, and perhaps you can't design blasting this finely, but bucket fill factor, where a lot of the overburden is pushed, you want some heave, and good fragmentation, but a D11 can carry so much more yardage if you don't have just total dislodgement of the material. Are there ever any studies? It would be impossible to predict, I suppose, but do you consider bucket fill factor at all in how much you dislodge the material?
I personally, I think you have to consider it. You know, you have a lot of different kind of ways to excavate the material, you know, whether it's a loader, hydraulic shovel, electric shovel, possibly some kind of excavator. You know, some are good at digging and some are just strictly scoopers. So I think you have to pay attention to your bucket fill time.
Yeah, it's not really necessarily the fill time, but the amount of bank cubic yards that you can carry with one blade load. If you've cast and really dislodged the material and it's laying out, well, the casting of course is good, but there's times when you can shoot the shot just perfectly that it's moved and dislodged, but the tractor will get more bank cubic yards, albeit they are loose in front of him, but the net is more bank cubic yards per hour out of a machine if you can shoot it that precisely, which is something I always strive to do.
Yep, no, I agree with you. I mean, there is a point to where you can shoot it, I think, way too much. Now you got way too much fines in there. So now you're moving actually more material than you should be moving.
You're moving lots of loose cubic yards and less bank cubic yards. And when it gets right down to it, bank cubic yards is what the bottom line comes to, yes.
Yep, I agree with you 100%. But I personally, other than we've done some fragmentation studies at certain places, you know, to try to find that optimum particle size. I mean, other than that, other than just actually tracking the performance of the machine on every single shot, and I think that's what lacks in a lot of operations I go to is you know, I've always had this belief that I've read this saying somewhere, but it says that if you can measure it, you can control it, and once you can control it, you can improve it. But you know, a lot of people don't measure, and a lot of people don't, you know, they just look at the shot and they just look at the numbers. They don't, you know, they don't record it, they don't compare it, they don't measure it enough to improve it, I guess is what I'm saying. And it's getting better and better in the industry as a whole, I think, of people doing that, but I still think there's a lot of places where that kind of lacks.
Okay, we have a couple more questions or comments. This one is from Robert Ingram. His comment was, and it was a little earlier, all geology has a specific sonic velocity based on the softness or hardness of the material. Emulsions have a high VOD and detonation pressure. As a result, they are well suited for improving fragmentation in hard, massive rock. On the other hand, ANFO is well suited for softer materials such as sand and softer geologies. Matching the VOD of the explosives to the sonic velocity of the geology is most always recommended.
Yes, and I would agree with that. Mm-hmm.
Here's a question from Brett Hunter. Is there a rule of thumb for using drill cuttings instead of crushed stone? How much more drill cuttings you would need to stem, say, a 4-inch hole?
That's a good question. I don't know if I'd have an immediate answer for that. Somebody else may be able to chime in. I think you could use the scale of depth burial formula, you know, and kind of get yourself in the ballpark and then see what adjustment you may or may not have to do with drill cuttings. You know, you may have to increase your stemming some to get the optimum amount of heave without, you know, too much confinement or the lack thereof. So I don't have a rock solid answer for that. If somebody does, jump in.
I'm going to tie Brad in here.
Ron, I think you're right. The bit about having to increase your stemming is what it really comes down to. I think about what the blaster needs and what they need to know out there. I don't know that you can see a difference in the weight of the stemming, but from a tested standpoint, if you're going to stem with crushed rock or something like that, and you have a pile of it sitting there waiting to go, try stomping on that and see how much that compresses. I used to remember Frank Chiappetta saying, you put a foot into a pile of cuttings, loose cuttings, ready to go down the hole or down the hole. You can put a pretty good footprint in that, and you calculate your weight by the area of the foot and so on, and say, well, that's so many PSI. And you won't be more than, you know, unless you're a horse like me, you won't be more than, you know, a few hundred PSI or something like that pushing on it. You look at that same borehole with that detonation pressure that starts to head into the millions of PSI, you know right away that that stemming is going to compress real fast and it's going to release. So you definitely want to look at increasing your stemming if cuttings are what you have. And then at some point you say, okay, that's reasonable for what I'm getting or the movement that I see in your video studies. But you want to be careful with switching from cuttings, for example, stone to cuttings, for example.
Thanks, Brad.
Got another question from Robert Ingram. He's raised his hand. So Robert, I'm going to unmute your microphone.
Okay, I just want to make sure you could hear me, Keith.
We can.
Okay, thanks. I didn't have a question. Just back to Brett's question. I think Ron did a good job on his stemming section there. But there's been quite a few studies conducted. I haven't been personally involved in them, but it's particularly any harder material application. If you have crushed stone, that's always your best bet. Unfortunately, like here in the Powder River Basin, you know, the coal mining companies aren't going to go to the expense of purchasing, you know, crushed limestone to stem these holes with out here. We, over the years, developed pretty good rules of thumb that Ron did cover regarding stem heights here, and all that has everything ties. The stemming all ties in with your burden and spacing, because as we all know, explosives are going to seek the path of least resistance. And if your burden and spacing is too large, that's most always going to be through your stemming. So it's all kind of intertwined, but certainly in hard material, you can always get the best top breakage without fly rock by using crushed stone. So good job on that, Ron.
Yeah, thank you. This is Rio. Yeah, it's didn't realize how many other places throughout the country actually use actual crushed stone for stemming, because pretty much 99.999% or better of the holes here in the Powder River Basin just use drill cuttings for stemming.
Down in the basin, like I said, we're shooting a much softer rock. Powder column doesn't usually tend to be as high. But if you did have an area where, you know, you had some kind of a tough cap rock or something on the top, and if you could get your hands on some good crushed gravel, it might, you know, it'll allow you to bring that powder column up and impact the top of that bench a little bit better. But as a general whole, you know, in most of your coal mines, stemming is primarily drill cuttings. But Bobby is right. There's not much better stemming than it gets when using like an angular crushed stone is just a very good stemming. I've even seen, was out in the iron ore range once, and they actually tried stemming. Those shots are so violent, there's no room for air, and they actually tried stemming with concrete. I don't know how well it worked. I don't remember, but they eventually, probably from a cost and a time standpoint, went back to what they were doing before, which is a byproduct of their plant, which is an extremely heavy sand, extremely heavy, and it seemed to work fairly well. But yeah, stemming is important, sometimes overlooked.
Okay, it looks like we're going to take a quick break here. We'll be back at 11:25, so about 8 minutes. Okay, let's go ahead and get started. I know Rio and Tony, you had a couple more comments here.
Yeah, I was wondering if Tony could explain the used oil a bit more.
Yeah, I definitely can. And Ron asked a question about me, or if we look at the densities of the fuel oil that we use, and we know what they are. I don't think we really play that in the scenario because the weights are pretty similar between everything we use, whether it's diesel and the used oil. But the one thing with used oil, you really have to pay attention to. It's basically the oil that they accumulate from PMs and things like that on equipment at the mine. They'll take that off site and then they'll clean it up and bring it back. But no matter what, that you're going to get debris in that. And that's where you run into problems more than anything, is your filters and your live strainers getting plugged and you're not getting that flow rate. So I wanted to point that out. And then another thing before we get too far along is Ron brought up something I was going to put in my presentation, is over-sensitizing emulsion, adding too many of those hot spots. Not here in Wyoming in the Powder River Basin with our weaker geology and things like that. That is very, you have to pay attention to that. If you over-sensitize or, add too many of those hot spots in, you can propagate with just the borehole pressure or the pressures created to the next hole, and it doesn't shoot according to your timing. You'll have multiple holes go off at once, and then you get into something called sympathetics. So that was another point I wanted to make. The last one, Brad brought it up in the comments here, but I think it's a really good thing is we had the gentleman come on talk about, bank cubic yards, moving it with your dozer and things like that. Well, when you calculate your cast to final, what we also come up with is a swell factor. So basically what you get after a cast versus what you had in the bank, and usually around the Powder River Basin, it's in the teens, the swell factor. But the higher that swell factor is, the more volume there is, basically. So when you're looking at that, trying to determine, I understand pushing more bank cubic yards is easier and things like that. That's probably a good number, is ask for your swell factor and see where you're at. And if you're starting to get into shots that seem to be pushing more bank cubic yards, talk to your engineer and say, hey, what was our swell factor on that? And you can design around that. That's basically all I had, Rio.
All right, thanks, Tony, for adding some more information on that. All right, go on to the next presentation.
Okay, great. Next up is Mike Mann, and he's from Ohio DNR, and he will be doing a presentation on effective microphone deployment methods on air blast measurements. Mike, I'm going to hand it over to you here.
There we are. Good afternoon, everybody. I see some names I recognize: Ken, Matt, Brian, Phyllis, and we got 2 Ohio certified blasters joining us too: Jason Fort, Jeremy Hazy. Shout out to them. And John Wiggin, I see you're watching. I'm glad. I hope you're still watching, because you didn't get to see this at the Kentucky conference. You couldn't be there. At any rate, let me expand this here. Now, are you seeing like a split screen where you can see my next slide as well, or are you just seeing just the slide?
We see the split screen.
Do you? Okay, let me get rid of that then. I've never done one of these like this before. There we go. Now, are you seeing the full screen?
Actually, we're seeing the one that you're not sharing your full presentation. It's just the back end.
If you hit the little button on the very bottom, Mike, the one that's a little book right next to the, go to the one to the left, right there, that one.
This one?
Yep.
Then what? Yeah, I have a split. I have 2 screens, and the screen on my right, I got the full blown version, and the one on the left is the development screen, the one you're probably seeing. And
the one on the right is the one that you can select that through the system there, Mike.
Oh yeah, how do I do that, I wonder?
it should give you an option of which screen. It kind of flashes on the screen which one you want to use when you're choosing.
I don't see any option here. Any suggestions on how to, so you guys can just see the full screen?
Let me pull out, and let's pull that out, and let's try it again here for you. And Mike, you should be able to make a decision on which side of the screen you want to use now.
Oh, I see. Great. Screen, yeah, screen and monitor 2. Now, what do you see?
That's what we've got, the full screen.
Oh, yeah. Sorry about that. All right. Yeah. So yeah, I'm with Iowa Department of Natural Resources. I've been a student of blasting seismology for 4 decades, but there's still stuff to learn, and that's being able to do special studies once in a while makes it fun to gain more knowledge and then share it. And yeah, I presented this first at the Kentucky conference, and then in February at the MSHA blasting seminar at the Academy near Beckley, West Virginia. And for that, we usually like to make it more of a workshop. So I added a little quiz to it, kind of liven things up. And so it is a handout. It's in the form of a handout with a fillable form if you wish. So take a few minutes to go through this. It's kind of like a pre-quiz kind of a thing, just to test your knowledge. And of course, I'm not going to see the results, so you don't have to be embarrassed by any means if you don't know something. Just and if all you can do is look at a screen, you don't have a computer where you can fill in an X on the correct answer, well, just go through them and visibly make a note in your head about what you thought the answer was, and I'll give you a minute or two to do that.
So just a little more explanation. This is Rio. If you, in your controls in the handouts, you open that up, and you should be able to open the handout that Mike is talking about. It should open up in Internet or Chrome web browser, whatever you have go in there, and then you can fill that in.
Yeah, at the Academy, I had everybody turn these in. I asked them not to change their answers, but no, don't put their name on them, and had them turn them in at the end of each class we did down there. And it was a little surprising. There was quite a lack of knowledge of basic facts about air blast and air blast measurement. So yeah, the idea is we'll go through some of these right away, and then we'll save some of them for you to discover the answer as we go through the presentation of the actual research study that we did. We'll give you about 1 more minute. Just take your best guess if you don't know something. All right, let's start looking at some of these. Oh, there we go. I had to click on the screen you guys were all viewing in order to advance to the next slide. Okay, so yeah, number one, air blast from a line blast is a compression wave. And hopefully that you're viewing actual live display there. But in the ground, we get compression and shear waves, but in the air, by the nature of air being what it is, it's only a back and a forward kind of movement, kind of like when you're in a traffic on the interstate, it comes to a halt and you kind of go bumper to bumper. The movement's always forward, but it's kind of one step at a time. Okay, so the air blast travels at the speed of sound, which on a warm spring day, say around 60 degrees for Montana, maybe, it would be about 1,100 feet per second. And the significance of that one significance of it might be to, if you want to estimate the distance to the seismograph using the air blast arrival time on a seismogram. And in this particular illustration, the air blast begins to arrive right here. If we assume that the ground vibration arrives at the very start of the record, which is minus 0.5 seconds on this on the second scale on the bottom, and we see that okay, there's 1 second, 2 seconds, and we'll call that about 2.2 seconds for the air blast to arrive after the ground vibration arrived at the seismograph. So if you take 2.2 seconds times 1,100 feet per second, you are approximately 2,400 feet from the blast, or from the blast to the seismograph. Now, a word of caution when you use this method, particularly at large distances. In this particular seismogram that we just looked at, now you're seeing more of the record, and you can see the actual distance was very close to 3,000 feet based on Google Earth and GPS coordinates and so forth. So you're looking at a deficit of about 600 feet, which would equate to about a half of a second. Well, and the reason that can happen, especially at long distances, is if you look at the particle velocities here, they're not real large, and those apply to the largest wave cycles. But you look out here to the far left at the start of the trace, you can see there was actually vibration prior to the start of the record. And the reason is that most modern seismographs, they will capture all the data a half second prior to the vibration that triggered the seismograph. So there was quite a bit of vibration, probably about a half second worth, that you're not even seeing on this record because it wasn't able to capture it yet. By the time it triggered, a lot of that had gone through. So just a word of caution, it's an estimation. It's not exact. It's not an exact method. Okay, as the air temperature rises, air blast travels faster. And if you think about it, when the air is cold and dense, it's going to be harder for that compression wave to push through it. So it's going to take longer. But as the air warms up, it's less dense, it's going to be a lot quicker, a lot easier for that pressure wave, that compression wave to transmit through that air. So which of the following air blast measurement units is based on a logarithmic scale? Well, the first three are all arithmetic, and the decibel scale is based on logarithms. And so it presents some rather strange things to deal with. For example, an increase of 6 decibels represents a doubling of air pressure. And to illustrate this further, here's an air blast conversion table where you can see this column here is millibars. This column is pounds per square inch. This column is in decibels. So if, for example, you've got an air blast of 120 decibels, or 0.2 millibars, and you double that air pressure, so 0.2, since millibars is an arithmetic scale, 0.2 times 2 would be 0.4 millibars. If you look up here, 0.40 millibars equates to 126 decibels, or a 6 dB rise. Similarly, if you look at the common regulatory limit of 133, that would equate to about 0.90 millibars, and half of that pressure, half the air pressure would be a 127. You down 6 dB, and you can see that you're roughly at 0.45 up to 0.9. So it works both ways. If you drop 6 dB from the limit, well, you've got half the air pressure. And yet, as many of you may know, 127 dB is more than enough to rattle people's cages, with or without ground vibration. Okay, so most of the energy, air blast energy from mine blasts, occurs at frequencies below the range of human hearing. So at birth, our hearing is supposed to be about 20 to 20,000 hertz. And note that the air blast, if you're monitoring next to a house, the air blast might not sound loud to you, but it can cause highly perceptible effects inside. And an example of how air pressure can affect a response to how a structure responds. In this case, we were getting a complaint from a lady who was very upset at a little over half a mile from coal overburden blasting, claiming that when she's sitting in, particularly in this corner actually at her dining room table, and a blast would go off, it would just rock the hell out of her basically. Even though it was a long distance complaint, we were curious to see what was going on, knowing that pillar supported type structures, piers, whatever you want to call them, tend to oscillate more than wood frame houses in our experience. So we gave her the benefit, and we had a seismograph where we buried the geophone in the ground, and we had a geophone attached to the upper corner of that house trailer. They were daisy chained together, so everything was time correlated. And here you can see the air blast arrival with the ground unit microphone, 119 decibels. The ground vibrations didn't amount to a whole lot. 0.05 was the maximum ppb. But this spike here at about 7 hertz really got that trailer oscillating in a back and forth motion across the short axis of the trailer. And you can see the actual displacement in the upper corner was pretty small, 0.009. That's roughly the thickness of 2 sheets of paper. But trust me, anybody sitting inside that trailer, it felt just horrible. Here's a time correlated matchup. Here you can see the air blast arrival, and here's the response of the trailer to the ground vibration. Not much at all. And then all of a sudden, the air blast spike about 7 hertz arrives, and the trailer starts oscillating around 5.5 hertz. All right, so the other answers to 7 through 10, you can get those from listening to the rest of the slideshow here. So why do we do this special study? Well, we just happen to have a state seismograph really close, set up close to a third-party seismograph a couple years ago. We were doing a special study of portal development, air blasts from portal shots, development shots, and a third-party blasting seismology firm happened to be monitoring outside the shop mainly for liability protection for the quarry. And so we saw over about a 6-month period a plus or minus 2 to 4 dB fluctuation between the two seismographs when it came to air blast measurements. And so this led me to wonder, so were the discrepancies because there were 2 different makes and models of seismographs? Well, if you look at the ISEE performance specifications for blasting seismographs, All these seismographs that we use are supposed to be created equal, so to speak, or at least give the same response within certain specifications. As an example, for air blast measurement, there should be a flat response from 4 to 125 hertz plus or minus 1 dB. So what does that look like? So here's a graphical representation of that. So if you look at how the microphone on this seismograph responded input-output wise, it's relatively flat between 4 and 125 hertz. And in other words, if your input, let's say at 4 hertz, right here, was say maybe 134, that seems to be one that White Industrial Seismology likes to use for testing, and Wigan probably does too at Vibronics. 134 was your input. Then at 4 hertz, you also got 134 as your output. That's the idea, plus or minus a dB. You can see it's starting to roll off as you go to lower frequencies here, and it's allowed to roll off considerably. And in fact, it's expected to be dialed in such that it does roll off between the heavy black lines as you go down below 4 hertz. Similarly, on the high end, you're allowed a roll off, although it's a little more generous, above 125 hertz. Of course, in most mine blasts, you rarely see anything this high anyway. So that's what that means by flat response between 4 and 125 hertz. So if we assume that the differences weren't because there were two different makes and models of seismographs, then the question becomes, was it the microphone deployment methods causing the discrepancies? So let's look at some examples of how microphones are deployed. Well, we've used this double windscreen, double rain shield method for decades, recommended originally by Larry Cornelius of LARCOR in Texas. In the last few years, I've seen a few of these rigid metal boxes with just two simple little holes on one end of the box. This more modern seismograph box with the solar panel, you can see the mic port on the side, and we're going to zoom in on that. If you take this filter plug out, you can see the barrel of the microphone is essentially flush with the outside wall of the box. So it's in essence, it's an external microphone port with an external filter, act as a windscreen. There's another method, and this would be a rigid steel box. It's got a huge ventilation on both long sides of the box, and the microphone is placed inside the box with the seismograph recording box and probably a battery and even a modem. Okay, this type of box is very modern, and on the opposite end, there it is. It too has an external mic port with that filter plug in it. And then I've even seen this style. Actually, I haven't seen this in the field. I went to the consultant's website and got this off of it. It shows a truly external microphone, presumably a modern one that's allegedly very water resistant, because all this has on it is a foam windscreen. And of course, it is sideways, so the likelihood of water sitting on the top of that screen and getting into to the microphone elements probably pretty slim. Okay, and then another common box that we see around parts of Ohio is this style, where you can't see it, but the sloped front of this box has a solar panel on it, and then in the back of the box there's a small hole where the microphone protrudes with a thin plastic bag over it, and my concern with that one, of course, is if it's facing the blast, the solar panel, then is this sheltered from the air blast somewhat? Here's another fairly modern box with the external type port with a filter plug, and this is on the bottom of the box. Okay, so now if we look at the ISEE field practice guidelines for blasting seismographs, pardon me. I've highlighted some things. The microphone should be mounted near the geophone with the manufacturer's windscreen attached. That's that foam. It may be placed at any height above the ground. Well, originally the field guidelines called for something a little strange, like, well, it's all right if the microphone is just above the ground, and it's all right if it's more than 3 feet above the ground, but anything in between apparently wasn't acceptable. Don't quote me, but it was something a little strange like that. So Elschlager and Wheeler did a study, and it was published in 2005, and essentially in the highlighting there, the microphone height has negligible impact on air overpressure measurements. That was their conclusion. There was also a study after that by some folks in a different country, and I forgot the reference I meant to include it, but it essentially confirmed their findings here. Okay, so the microphone should not be shielded. And again, that's why I was a little concerned about this style of box here. And the orientation of the microphone is not critical for air overpressure frequencies below 1,000 hertz. Now, there is a reference given in the ISEE guidelines, and that reference is right here. It's from the U.S. Bureau of Mines RI 8508, and you can read what's highlighted there. But what was always curious to me is that in RI 8508 there was never any reference made to where this came from, that just never sat well with me. I would like to have seen some real data or where they actually got that from. And more on that later. Okay, so the microphone element must be kept dry with a thin plastic bag or rain shield. And this stuff was just added, by the way, in the last go-around, the last time that our committee made some changes to the guidelines. And here's some additional information. The rain shield should be tied loosely, and completely sealing a rain shield could result in the following. You can have condensation, static pressure, rain triggers, and of course, if you've got condensation and the moisture stays inside the microphone, it's going to ruin the element eventually. Okay, so what about security boxes? Well, this was also added in the last go-around, the last modification, the revisions to the guidelines. So it says microphones inside security boxes, they're okay as long as the pressure change in the enclosure reflects the pressure change outside. So, I got to wonder, is this enough ventilation here compared to where you got large vents on both sides of this long box? All right, so the deployment study procedure, we use seismographs of the same make and model for the testing. We started with mic quality control tests. We compared 3 deployment methods side by side against the control. The control was a mic with just a foam windscreen, and the 3 deployment methods, you'll see examples later, we were able to borrow security boxes from 3 third-party consultants. And we sought a variety of mine blasts producing varied air blast frequencies and waveform characteristics. We randomly selected the pairing of serial numbers with deployment methods for each test blast. So we didn't always have the same seismograph serial number as the control or as one of the other boxes. They were randomly selected for each test. Okay, so the microphone quality control test, we took 7 of the same make and model seismograph, and we did 2 tests. One had lower frequencies, the other had some higher frequencies from 2 blasts, and we picked the 4 that were within a half dB of average, which I thought was surprisingly good that we're even able to find 4 units that were that close. And the waveforms looked essentially identical as well. It wasn't just the amplitude of the air blasts that were plus or minus a half dB. Okay, so here you can see the security boxes that were on loan. These 3 boxes, here's the control. And for discussion purposes, we'll call this the red box, yellow box, blue box. And for every test, we set these up the exact same way. We had this box, worst case scenario, we had the external port directly away from the blast. For this box, we always had the external microphone directly away and quote, sheltered from the blast. And for this box, we always had the long sides, how should I put it? The long side would be pointed towards the blast, so to speak. So your vents were on the sides. There's no venting on either of the short ends. And then the microphone, of course, is inside that box. Here's a view from the front side, just to get a better idea how things looked. Inside the red box, you can see the external mic port. And of course, that filter plug would be just outside of the box. Inside the yellow box, the solar panel, of course, is when you flip this door down, it's on the back side of it. But there's the mic port where the microphone is stuck through the back of the box. The blue box with the vents, you can see the large ventilated area. And there's the microphone with just the windscreen. It's basically just in the middle of that big box. So the summary of the test conditions, we did 30 test blasts between January and August of 2019, spanning 14 quarries and 4 coal mines throughout Ohio. Blast distances range from 135 to about 1,900 feet. And we had peak air blasts ranging from 122 to 143 dB. We pretty much guesstimated at each mine site where we might get a reading around 133 dB, give or take. And we did pretty well because 17 tests out of 30, we were able to get air blasts in the 130s. And there was even one test where I think we were about 1,600 feet from a large quarry shot, very energetic. And it actually pegged the needle on all 4 seismographs. So we had to throw that data out. They're all 148s right across the board. Peak air blast frequencies range from 2 to 102 hertz. And to give you an example how that broke down, you can see most of the tests fell within like 4 to 10 hertz in this area here, and that's probably good because that's most mine blasts they're going to be somewhere in that range of say 4 to 20 or so hertz, whether it's quarries or coal overburden shots. Some of the small quarries where they're using real shallow holes and very little stemming, then you're going to see some of this. You're going to see some really high air, a lot of rifling and high air blast spikes that are sometimes well over 40 hertz. Okay, so Ken Elschlager plotted the data for me, and I want to point out that you're looking at the results of all 30 tests here. It's kind of like an individual scatter diagram for each test blast. You can see the legend up here, red box, yellow box, blue box, control. We're going to zoom in on this to make it more clear, but don't worry about the slope lines that connect. That's just to kind of give some connectivity to all the tests. It has really nothing to do with anything, but just to kind of string everything together. But here's your decibel scale to give you an idea where each test fell. All right, so we're going to enlarge this particular result for that particular test, which is what, test 11 or 12 or something like that. There we go. So there's the black dot. Let's start with that. That was the control unit reading for that test blast at 142.8 dB. Getting ahead of myself. The red box was 143, just a little bit above it. The yellow box was a little bit below, and you can see what the hell happened there? Sorry about that. There we go. You can see a control ring plus or minus 1 dB from the control reading for that test. And you can see the blue box was a little high for that test at 144.3. Right, so now let's look at just the red box. How did it do? Okay, you can see that for just about every test, the red box fared pretty well. It was either very close to the control, meaning the black dot in the middle of each of these gray circles, or it was maybe on the outer edge of the gray circle, and maybe like here, it's just touching the outer edge of the gray circle. Quite consistent. The least consistent happened to be where the peak control air blast, the peak was only 2 hertz, which way below the roll off, below 4 hertz. So we might even discount that one a little bit. All right, let's look at now the yellow box. For the yellow box, the trend was to see lower readings than the control. And I've put a red arrow, and there's 5 tests where it was significantly below, the measurement was significantly below the control air blast reading. And for the blue box, almost conversely, the trend was to see slightly higher readings, and for 3 of them with the red arrow, they were significantly above the control. So to summarize the findings, the red box recorded air blasts consistently close to the control. And interestingly, the mic orientation truly is not important based on the red box with its mic port always facing away from the blast. So I'd say now there's finally some empirical data to support what the Bureau said a long time ago and what the ISEE field guidelines picked up on. Okay, for the yellow box, however, it recorded in 5 of 30 test blasts, air blasts that were 3 or 4 dB lower than the control. For the blue box, they're in 3 of the 30 tests, the readings were 3 or 4 dB higher than the control. So you're already thinking, gee, which security box do I want to rely upon, right? If I'm a blaster and you're relying on a third-party seismograph for compliance. Okay, in 3 tests where the control air blast was less than or equal to the common regulatory limit, 1 box recorded 134 or 135. In 3 tests where the control air blast was 2 or 3 dB greater than the limit, 1 box recorded an air blast at or below 133. So you can see the above observations, and I might not be critical in terms of blasting damage potential, but could certainly be critical for compliance. Now, after that sequence of testing, I was curious, looking back at the, which box was it here? This one. How much did perhaps that thin plastic bag have to do with the trend for lower readings? I was also curious about the method we've been using for decades, the double windscreen and rain shield method. There's actually 2 windshields. One fits inside the other. You just can't tell. And a little bit curious too, the ISEE is saying use a rain shield over that windscreen. So, I'm curious, well, what effect does that have? And we wanted to go to a perforated plastic box. We've been using these nice big plastic boxes for a while, but we've had external microphones on posts, and there's problems that you get into with those, primarily from a maintenance standpoint. And people clipping the cables once in a while with weed whackers and so forth. So we wanted to be able to perforate the heck out of this box and know that we're going to get essentially the same reading. Okay, so we did 14 test blasts at 8 quarries and 3 coal mines, frequencies from 3 to 39 hertz. Most readings were plus or minus a dB of the control. None was greater than about plus or minus 2 dB. And here's a view of the inside of the perforated plastic box. So I already kind of explained all this, what we wanted to test and why. we heard all that. You heard all that already. Okay, so yeah, Ken plotted this one for me too, and in a similar fashion, you can see very quickly that overall, all three methods compared, I thought, pretty well with the control. Nothing like 3 to 4 dB like we saw with, higher or lower with those two different security boxes. Okay, so the gosh, are we really doing that well for time? I must be going through this thing awfully fast. We're scheduled to end at 1/4 after the hour. Is that correct, Rio? Keith? Hello?
Yes, that's correct.
Okay, thank you.
Yeah.
I'm beginning to wonder, has anybody heard any of this? Okay, all right. So prior to doing the main study with the 30 tests and the 3 different boxes, I had bought a steel box at, like, I don't know, Tractor Supply or somewhere like that, and I drilled a couple of 1-inch holes on the side to simulate that one type of box I had seen earlier. You saw in an earlier slide, and we'd already acquired from the third-party consultant this style of box. So we did a number of test blasts with 4 different, the same make and model, but 4 seismographs, and we ran into some problems. And when it was all said and done, I realized, looking back, we didn't start with 4 boxes that were giving us really close readings to begin with, like we did for the main study. So basically, I essentially discounted the early study, and I'm calling it a prequel or a pilot study. But we did see one very interesting result that I'd like to share with you. And in this particular test, we're maybe 350 feet or so from a coal overburden blast just over the crest of this little hill. We happen to be set up on an asphalt driveway near a house, the nearest dwelling. And pardon me. Here's the control, although you won't see the microphone because when I thought to take a slide, their little puppy had already pushed it over, I think is what happened. That was after the test, actually. And here's our single foam windscreen, single rain shield, and external microphone off the back of this one. Okay, so in this particular test, the control measured a 122, the steel box a 122, and this box oddly was higher. Remember, in the major study, it trended lower. Very curious. Well, and then if you look at, okay, here's the control unit results. Again, here's the control over here, just a foam windscreen. You can see that the direct air blast arrived right here, and it was 122 decibels. You can also see on the vertical direction of ground motion, there was some high frequency pulsations, and at about, this is saying 32 hertz, and you can see that here on the FFT right here. That would be this peak right here. And the vertical oscillations drove what you're looking at here, what we call a rock pressure pulse that the microphone picked up, the control microphone. But in this case, the direct air blast, or what I like to call true air blast, was much greater than the effect from the rock pressure pulse. Now, look at what the yellow box did. Here again, here's the vertical oscillations at high frequency, and look what it produced on the front end before the true air blast arrived. And you can see that the asterisk that shows the highest cycle there at 126 decibels was 3 dB higher than the true air blast at 123 dB. And what's happening, of course, is we're theorizing that the oscillations at that high frequency transmitted through the steel framework through the steel clamp into the metal microphone barrel of the microphone and cause that response in the microphone. But it actually caused a higher air blast, so to speak, than the true air blast arrival by 3 dB. And this is something that over the years it's been kind of anecdotal, because I've heard consultants say occasionally they've seen this sort of thing happen, but they don't, in those cases, they don't have another seismograph as a control side by side with it. In this case, we happen to have the control unit, so it was very clear that what third-party consultants have said happens once in a while does in fact happen, and that's proof of it. So to wrap up, recommendations: microphone deployment methods should be thoroughly tested. Test them with an array of frequencies and overpressures from actual blasts. Make necessary modifications like damping steel boxes, increasing ventilation, relocating external ports to increase exposure, whatever it takes. And then keep records of those results for reference. And that's it. Any questions or comments? I guess, do I need to open up the well, you'll tell me if there's a question, right?
Absolutely, Mike. Thank you.
Okay.
Yeah, if anyone has any questions or comments, you can write your questions in the system or raise your hand.
Hey, Mike, this is Rio. I do have one question for you. If you're going to buy an enclosure for seismograph, which one would you buy?
Okay, well, without mentioning brand names, I would say I would buy any box that has an external, and I'm trying to go back to the pictures, any box that has essentially an external port like this with the filter plug, and that is not tremendously sheltered by anything. And apparently, like this example here, must not have been too sheltered, or it wouldn't have done so well. And then, of course, in the beginning of the show, you saw other, there's what it looks like from the inside. You saw other, examples of other modern boxes with external ports with the filter plug. One was at the bottom, and I've seen them on the top, I've seen them on the sides. But I think the key is that, number one, they are external, and number two, they're not sheltered too much as I think this one is. Does that answer it for you?
Yes, it does. Thanks.
Hey, Mike, we do have a couple questions here. The first one is going to be from John Wiegand, I think, and I apologize. I'm going to unmute your mic, but I apologize.
Hold on a minute here.
You might want to turn down
Sorry about that. Hey, Mike, it's a very good presentation. It's good to hear from you.
Yeah, likewise, John. Sorry I missed you down in Kentucky.
Can you hear me?
Yeah. I can hear you. Hello?
I can't hear you.
John, we can hear you.
Let me look at something real quick. I'm sorry. I think I've got an issue with my...
John, we'll come back to you.
Can you hear me now?
I hear you. Hello, John.
Mike. Oh, I'm sorry.
I hear you.
I'll just make a comment then if you can hear me. Mike, it was a real good presentation. I think it's something that is very valuable. The thing I wanted to comment on, if you can hear me, is the fact that it's not really all that uncommon to see that mic response like what you picked up. And we see that quite often, and I believe there's a couple reasons for it. Number one, some people's microphones, some manufacturers' microphones are probably more sensitive to a vertical motion in the element. The other thing is the fact that the frequency that the ground vibrations that we see on the vertical, if we have a high frequency on the vertical, then a lot of times we see that come through on the microphone. We see the high frequency response to the vertical ground vibration. And I apologize, I can't hear you, but I just wanted to make that comment. And I think this is a very good study that you did.
Thank you, John. I'm assuming you can't hear me talking, but yeah, I suspected when we saw that frequency response that there's certainly a certain frequencies where that microphone barrel is going to resonate more than at others.
Do we have any other questions or comments from the attendees? Okay, well, thank you very much, Mike. We do appreciate it. Rio, I'm going to hand it back over to you.
Well, thank you for attending the second session here. On my screen, I have the my contact information. If you desire to receive blaster education for this webinar, please fill out the affidavit of attendance and return that to me. Again, thank you to all the presenters. I think it was a really good session.
Hey, also, it looks like we got a last minute question from Robert Ingram. Robert, I'm going to unmute your mic.
Yeah, you got me now?
We do.
Okay. Hey, I don't want to get too detailed here, Mike. I had a couple of questions just for understanding purposes. So we have all these seismographs set up to kind of check each other. What was all these different shots? Was there any records of the wind direction or velocity from left to right from the shot to the seismographs, and also on the shot orientation in relation to the position of these seismographs machine? Were these always facing the face of the shot, or were there times maybe where the shot face was perpendicular to the setup of the machines? I was just curious.
Yeah, I don't know if you can still see my screen, but I went back to the slide to show the setup that we used in each case, in every case. Yeah, there you go. Oh, wait a minute. Let me hit the show my screen. There we go. Can you see it?
Yes. I was just curious. I assumed that they were all pointed at that face. I just wasn't for sure.
Yes. No, the other question is a little more difficult to answer because I have to admit we did not keep good records of wind speed and direction. But I guess part of our assumption there was that all boxes, were subject to the same wind speed and direction during every test. And I know there were a few tests where there were some significant winds. And I don't recall if one of those happened to correlate with, a higher or lower reading with one of the boxes. I'd have to really go back and look. But all in all, for most of those 30 blasts, we weren't dealing with extreme winds by any means. Typically maybe 0 to 5 or 5 to 10, kind of in that range. And there were times too where it was breezy, but then moments before the shot, things would settle down and be very calm even. That's the best I could do to answer that one.
No, that's okay. I'll try to be brief here. But in your professional opinion, with the wind speeds that we have out here from time to time, 10 to 15's just a normal day, but we have the days where it's 25 or 30 blowing. Would crosswinds in your picture here you're showing, would a crosswind here, in your opinion, what effect would that have on the air blast readings at 25, 30 miles an hour?
It would be pure speculation, to be quite candid with you. But yeah, I kind of have that same question, and for example, that long box with the vents on the two long sides, if you did have a strong crosswind, who knows, maybe that would create a higher reading in that box than one of the others. Of course, you know, one of the reasons we use foam windscreens is to reduce the impact of wind. But I also know from, you know, 40 years of doing monitoring that when you get really strong winds, even if you have a windscreen on there, if you've got it set, say, on a acoustic trigger level of 130 dB, which we often do, you're going to get a lot of wind triggers. So yeah, so it would just be speculation there to answer your question.
Okay, well, thanks for your answer.
You're welcome.
Any other questions or comments? Looks like that is it. Rio, I'm going to reshare your screen.
Okay. There is my contact information if anybody needs my email or my phone number. Again, thank you for coming, and we'll be seeing you guys. We'll be having another one of these sessions October 6th of this year. So I'll be sending out a link to that as well. Thank you.